For hundreds of millions of years, Earth looked nothing like the world we know today. 400 million years ago, vast shallow seas covered the continents, strange armoured fish ruled the oceans, and the first forests were only beginning to take root on land, quietly reshaping the air itself. Today we travel back to this ancient Devonian world to see how our planet looked in its age of fishes and early forests. If you enjoy peaceful journeys into deep time, please subscribe and share, and tell us in the comments, what part of Earth's distant past are you most curious about? Thank you for watching. Now let's begin. In this documentary, Earth is considered at a specific interval of geological time around 400 million years ago during the Devonian part of the Paleozoic era, and the first layer of that world is its setting in space. At this time, Earth orbits the Sun within a mature solar system, whose main arrangement is already familiar small rocky planets in the inner region, gas and ice giants farther out, and belts of smaller icy and rocky bodies beyond them. The distance between Earth and the Sun is close to that of the present day, so the planet continues to receive a similar share of solar radiation, even though the Sun itself is still evolving as a main sequence star and is slightly less luminous than in the modern era. The difference in luminosity is modest because several billion years of stellar evolution have already passed, and the Sun has moved partway along its slow track of increasing brightness without yet reaching any extreme state. The solar system as a whole moves around the centre of the Milky Way galaxy on a wide, slowly changing orbit. The exact position along that galactic path at Devonian time is not known in detail, but there is no strong evidence that Earth is passing through an unusually dense or unusual part of the galaxy at this interval, so the broader stellar environment can be treated as broadly comparable to the present one in terms of overall radiation background and the distribution of nearby stars. In this Devonian interval, Earth itself has already existed for more than 4 billion years, and many of the large-scale aspects of its physical behaviour are recognizable. The planet rotates once on its axis in less than a modern day, and it completes one full orbit around the Sun in roughly the same span of time that defines a modern year. Its axis is tilted relative to the plane of its orbit, so the angle between the rotational axis and the orbital plane gives rise to alternating seasons as different latitudes receive differing amounts of sunlight through the course of an orbit. The size of this tilt called obliquity is similar in order of magnitude to the modern value, although exact numbers at any given Devonian moment are not known, and the tilt can vary on long-time scales due to gravitational interactions with the Moon, the Sun, and other planets. Because the planet spins more rapidly than it does today, the length of one rotation is somewhat shorter, and the number of rotations that fit into a single orbit around the Sun is somewhat greater, so there are more shorter days within each Devonian year. This state follows from the long-term exchange of angular momentum between Earth and the Moon, under the influence of tides in the oceans and solid Earth. Over hundreds of millions of years, tidal friction slowly transfers rotational energy from Earth to the Moon's orbit, gradually slowing Earth's spin and causing the Moon to move outward. In the Devonian interval, this process is well underway but not complete, so the Moon orbits closer to Earth than it does now, and moves across the sky slightly larger and more quickly. As a result of that closer distance and the faster spin of Earth, tidal forces are somewhat stronger, and the timing of tides differs from the modern pattern, but the basic rhythm of periodic rising and falling of sea level along coastlines is already established. The daily cycle of daylight and darkness proceeds as Earth turns, and the seasonal cycle operates as the axis tilt and orbital motion combine to shift the latitude of maximum solar input over the year. Because the length of the day is shorter, the apparent motion of the Sun across the Devonian sky is a little faster than in the modern world, but the sequence of sunrise, midday, sunset, and night remains the same in structure. The amount of solar energy that reaches the top of Earth's atmosphere, often called the solar constant, is modestly lower than the modern value reflecting the slightly lower luminosity of the Sun at this age. If all other conditions were unchanged, such a difference in input would tend to make Earth somewhat cooler. But all other conditions are not unchanged, because both the composition of the atmosphere and the arrangement of continents differ from those of the modern planet. The influence of those internal factors belongs to the domain of climate and surface processes, rather than to the outer orbital setting described here. At the scale of the solar system, what matters is that Earth remains inside the circumstellar region, where liquid water can exist on its surface for long spans of time. Geological evidence independently shows that stable oceans and surface water bodies exist long before this Devonian slice, and continue through it, indicating that the balance between solar input atmospheric properties and planetary heat loss is compatible with a hydrosphere that does not fully freeze or fully evaporate. Gravitational interactions with the giant planets continue to influence the paths of comets and asteroids, and over long periods, this leads to occasional impacts on the inner planets, including Earth. The available record does not point to an exceptional concentration of very large impact events, centered narrowly on this time interval, so such collisions are treated as part of the rare but ongoing background of external disturbances, rather than as the main agent setting global conditions. Another important feature of Earth in space is its magnetic field, generated by motion of conductive fluid in its metallic core. This field extends outward and interacts with the solar wind, forming a magnetosphere that channels and deflects many charged particles. Devonian rocks preserve evidence that such a field is present, including indicators of polarity reversals and changes in field direction through time, but at the broad level relevant for this outer view. The key fact is that Earth carries a global magnetic shield that limits direct exposure of the atmosphere and surface to the solar wind. Variations in the strength and structure of the field over geological time can influence the flux of charged particles that reach the upper atmosphere and may have subtle consequences for atmospheric chemistry. But there is no firm evidence that the general existence of the field is interrupted during this interval. Taken together, these features define the cosmic setting of Earth around 400 million years ago as that of a rocky planet orbiting a main sequence star at a distance that supports long-lived surface water, rotating somewhat faster than at present, accompanied by a closer moon subject to the gravitational influence of other planets and smaller bodies, and enveloped by a magnetic field that forms a protective cavity in the solar wind, all within a stable, long-lived region of the Milky Way galaxy. At the Devonian interval around 400 million years ago, the solid outer shell of Earth is arranged into large tectonic plates that carry continents and ocean floors, and their pattern defines the global geography. One of the most prominent features is the great southern landmass known as Gondwana, which extends across much of the southern hemisphere. Its outline includes areas that will later correspond to South America, Africa, Antarctica, Australia, and parts of Asia and the Arabian region. Gondwana is not a simple block, but at this scale, it can be treated as a vast composite continent, bordered by long convergent margins in some sectors and by passive, slowly subsiding margins in others. Superimposed on that southern landmass is a wide range of regional basins and uplifts, but these details belong to later, more local views. For the present layer, the important fact is that a single dominant continental assembly occupies much of the southern high and middle latitudes. Closer to the equator, another major continental mass is present, Euramerica, sometimes called Laurussia, formed by the collision and welding of earlier components that include parts of what will become North America, Greenland, and Europe. During the Devonian, this continent lies near low to middle northern latitudes, rotated and shifted compared with its modern fragments, and bordered by shallow seas along many of its margins. Between Gondwana in the south and Euramerica nearer the equator, as well as between Euramerica and other smaller continental blocks farther north and east, there are broad ocean basins. Some of these basins represent remnants of older oceans that are in the process of closing through subduction, while others are more long-lived expanses that will persist into later periods. The names used by geologists for these basins, such as the Reich Ocean, the Paleotethys region, and early parts of the Panthalassa expanse, reflect their positions between particular continental configurations. At this stage, the basin that will later grow into the vast Panthalassa Ocean already occupies a very large area of the planetary surface, covering much of the hemisphere opposite the combined Gondwana and Euramerica masses, and enveloping smaller crustal fragments. North of Euramerica, separate blocks including Siberia and various microcontinents stand apart, each with its own surrounding shelves and slopes, and their future collisions will contribute to later mountain building, but at this point they remain distinct elements in a broader mosaic. The distribution of these continents and ocean basins is inferred from a combination of paleomagnetic data, fossil distributions, and structural histories, and although the exact outlines and positions carry uncertainties, the general pattern of a large southern supercontinent, an equatorial to mid-latitude northern continent, and intervening and surrounding oceans is well supported. A key feature of Devonian geography is relatively high global sea level, which results in extensive flooding of continental interiors and margins. The upper parts of many continental shelves, especially along Euramerica, are submerged beneath shallow epicontinental seas. These are broad, low-gradient marine environments that can extend hundreds of kilometers landward from the shelf edge, with water depth typically measured in tens of meters rather than in kilometers. The flooding produces long indented coastlines and complex networks of inlets, embayments and low-lying marine platforms. Over parts of Gondwana, similar shallow seas occupy subsiding basins and peripheral margins, although in other regions the continent remains emergent and supports land-based environments. Where continental crust lies closer to the equator, solar input is greater, and the shallow seas over those margins tend to be warmer. Where it lies nearer the poles, conditions are cooler, but the overall Devonian climate context is addressed in a later layer, so it is sufficient here to note that broad belts of shallow water environment follow latitude and plate position. The boundaries between tectonic plates mark zones of significant crustal interaction that also influence geography. Along some edges, plates move apart and create spreading centers where new oceanic crust forms, building long submarine ridges that stand above the general abyssal plains. These ridges interrupt the continuity of deep basins and provide elevated seafloor topography, though they usually remain beneath ocean waters and do not directly create major land masses at the surface. Along other margins, one plate descends beneath another, producing subduction zones with deep ocean trenches and volcanic arcs. In the Devonian configuration, such convergent boundaries occur along segments of the margins of Gondwana and around other blocks, and over long time scales they contribute to continental growth and mountain building. In the far northern and far southern latitudes, some of these convergent zones are associated with active orogenic belts. But from the high global viewpoint here, what matters is that continents are edged by a mix of passive margins with wide shelves, and active margins with trenches and volcanic arcs. On the continents themselves, the pattern of mountain belts and lowland basins, though important for regional landscapes, remains secondary to the large-scale separation of land and ocean. However, one should note that parts of Euramerica, especially those formed during earlier collisions, already host significant uplands and uplifts that influence regional drainage and the distribution of sedimentary basins. These uplands will later be further reshaped by continuing tectonic events, but in the Devonian their presence already helps to organize the flow of rivers from interior high areas toward coastal plains and shallow seas. The arrangement of land at various latitudes interacts with the shape of the ocean basins to define several major climatic and oceanographic belts. Yet at this layer the focus remains on geometry rather than on circulation. There is a concentration of continental area in the southern hemisphere through Gondwana, an important equatorial to mid-latitude continent in Euramerica, and a relative sparseness of large land masses in some other bands, with smaller blocks occupying those positions instead. Broad oceanic realms separate and surround these continents with deep basins occupying most of the planetary surface. The exact outlines of the continental shelves and the detailed shapes of the coastlines shift over the span of the Devonian, due to sea level variations, sediment supply, and ongoing plate motion. But over the narrower interval around 400 million years ago, they can be considered relatively stable at the scale of tens of millions of years. As plates move at rates of a few centimeters per year, their positions change gradually. Over the length of a single human lifetime, this would be imperceptible, but over Devonian time spans, it is sufficient to bring continents into and out of collision, and to open or close ocean gateways. For the present time window, the simple description is that a large southern supercontinent, a substantial equatorial to mid-northern continent, and several smaller northern and equatorial blocks coexist with extensive interconnected oceanic basins and wide shallow seas that flood many continental margins and interiors, forming the geographic framework within which atmosphere, climate, surface environments and life operate. The atmosphere of Earth around 400 million years ago in the Devonian interval is a mixture of gases broadly similar in kind to the modern air, but different in proportions, and this composition, together with the distribution of land and sea, controls the global climate of the time. Nitrogen remains the dominant constituent and makes up most of the atmospheric mass, providing background pressure and acting as a largely inert buffer gas. Oxygen produced over long spans of time by photosynthetic organisms in the oceans and by emerging land plants is present at a substantial fraction of the atmosphere, though its exact level at this particular interval is uncertain and varies among different reconstructions. Many lines of evidence, including models of carbon cycling, and the presence of large plants on land indicate that oxygen is lower than in the richest peaks of later periods, but higher than in very early Paleozoic ages, placing this Devonian slice in a middle range where combustion is possible, and large aerobic organisms are supported, but where the air does not yet carry its highest known share of oxygen. Carbon dioxide, a greenhouse gas that absorbs and re-emits infrared radiation, is present at levels significantly above those of the modern pre-industrial atmosphere. Estimates of its concentration carry considerable uncertainty, but most studies indicate that it is several times higher than modern values, especially earlier in the Devonian, and this enhanced greenhouse forcing helps maintain warm global conditions despite the slightly reduced luminosity of the sun at this time. Alongside these major gases, the atmosphere contains water vapor argon, and trace components such as methane, nitrous oxide, and various reactive species, but their exact concentrations are poorly constrained for this interval and are usually treated through models rather than direct measurement. The total surface pressure of the atmosphere is thought to be broadly comparable to that of the modern world, though some hypotheses allow for modest deviations. There is no firm evidence for an atmosphere that is many times denser or much thinner than today. So for the purposes of describing Devonian climate, it is reasonable to consider surface pressure as lying within a range of values that still support stable liquid water oceans and normal weather systems. Under these conditions, the global climate is generally warm, and the planet is often described as being in a greenhouse state. There is no strong sign of large permanent ice sheets covering extensive high-latitude regions during much of the Devonian, though there is evidence that toward later Devonian times intervals of cooler climate and even glacial activity occur in some parts of Gondwana. within the narrower window around 400 million years ago. Considered here, the prevailing picture is of oceans that are largely ice-free, especially at low and middle latitudes, and of continental margins experiencing temperate to warm temperatures, modulated by latitude, altitude, and proximity to the sea. Because Gondwana occupies much of the southern hemisphere, and Euramerica lies near the equator and into the northern hemisphere, the arrangement of land and sea alters patterns of heat storage and transport compared with the modern world. High sea levels mean that warm, shallow epicontinental seas cover large areas of the continental surfaces, and these shallow waters act as heat reservoirs that absorb solar energy and release it slowly back to the atmosphere. This configuration damps some seasonal extremes near flooded margins, and allows marine influences to extend far inland over continental platforms. The latitudinal gradient of temperature, meaning the difference in average conditions between equator and poles, is still present but somewhat reduced compared with many later periods that host large ice sheets. Equatorial regions receiving the most direct solar radiation are warm to hot and support vigorous evaporation and deep atmospheric convection. Rising air in these low latitudes gives rise to large-scale circulation cells that transport heat poleward, where air cools and descends at subtropical latitudes, then continues toward higher latitudes near the surface. This broad pattern resembles the modern Hadley Ferrel circulation, but is modified by the different distribution of continents, the higher greenhouse forcing, and the presence of wide, shallow seas. Over Gondwana, especially at middle to higher southern latitudes, temperatures are cooler than at the equator, and regional climate depends strongly on whether a given area lies near a flooded margin, a shallow inland sea, or a more elevated interior. Some sectors may experience relatively humid conditions with frequent rainfall, driven by onshore winds and convergence of moist air masses, while others maintain more seasonal or even semi-arid regimes where continental interiors lose moisture to distance from the coasts and to rain out along prevailing wind paths. Over Euramerica near the equator, widespread shallow seas and low-lying coastal plains help produce warm, moist climates along many margins, favouring persistent cloud cover and frequent storms, while interior uplands may experience slightly more seasonal temperature and rainfall cycles. Because much of the land area lies in lower latitudes, the belts of tropical and subtropical climate occupy broad zones, and there is a relatively narrow extent of very cold conditions at high latitudes. Precipitation patterns follow from these circulation structures and from the configuration of land and ocean. Regions under rising branches of large-scale circulation and near warm seas receive abundant rain supporting river networks and wetlands, while areas under descending dry air or in the lee of uplands receive less. The overall global water cycle is strengthened by the warm climate, because higher temperatures support more water vapour in the air and more vigorous evaporation from the ocean surface and flooded shelves. Storm systems, including tropical cyclones and mid-latitude depressions, form over warm waters and move along preferred tracks set by prevailing winds and pressure patterns. But the detailed statistics of their frequency and intensity cannot be reconstructed with confidence, so they are treated here as part of the ordinary variability of weather rather than as unique features. Overlying all these regional variations is the long-term influence of land plants on climate and atmospheric composition. By the Devonian interval considered here, vascular plants with root stems and leaves occupy significant portions of lowland areas, and in some regions tree-like forms create early forest ecosystems. Through photosynthesis, these plants draw carbon dioxide from the air and release oxygen, while their roots and associated microbial communities enhance chemical weathering of rocks, which in turn can draw carbon from the atmosphere into dissolved forms carried by rivers to the sea. Over geological timescales, such processes can lower atmospheric carbon dioxide and influence climate, but their net effect at any particular moment depends on a balance between sources and sinks of greenhouse gases, including volcanic outgassing and burial of organic matter. The exact trajectory of carbon dioxide levels through the Devonian is not known in detail, and there are indications of significant fluctuations, including possible declines associated with episodes of enhanced organic burial and plant expansion. For the present description, it is sufficient to note that the atmospheric composition and climate state around 400 million years ago reflect a balance between a still strong greenhouse effect and the growing but not yet dominant influence of extensive forest cover. The resulting climate is warmer than that of the modern world, with ice-free or nearly ice-free conditions at many high latitudes, broad warm shallow seas and extensive humid low latitudes, while still allowing regional climatic diversity and temporal variability that play out over seasons, years and longer intervals. These atmospheric and climatic conditions form the background against which surface environments, ocean systems and ecosystems operate in this Devonian world. At the Devonian interval around 400 million years ago, the surface of Earth presents a set of broad environmental zones, whose arrangement follows from the distribution of land and sea, the prevailing climate and the level of the oceans relative to continental crust. The largest single domain is the open ocean, which covers most of the planetary surface, and includes both deep basins and the flanks of long spreading ridges. These deep basins are floored by relatively young oceanic crust, blanketed in many places by fine sediments that settle through the water column. The ocean surface above them is shaped primarily by wind and by large-scale circulation, driven by temperature and salinity contrasts. But at this layer it's sufficient to note that vast regions of the planet are occupied by deep water, whose surface conditions differ little whether they lie above a ridge flank or a broad abyssal plain. Closer to the continents, the seafloor rises toward the continental margins, forming broad shelves and steeper slopes. The shelves are relatively shallow, with water depths commonly in the range of a few tens to perhaps a few hundreds of meters, while the slopes drop more rapidly toward the deep basin floors. In the Devonian configuration, global sea level stands high. Relative to the average level of the continents, so many shelves are drowned and support extensive shallow marine environments. These continental shelves differ from the open oceans in several systematic ways. They are more strongly influenced by sediment delivery from land by tidal currents that are enhanced by the geometry of the coastlines and by waves that can stir the entire water column during storms. Some shelves, especially those near the equator and at low latitudes, are warm and receive abundant sunlight through much of their depth, creating broad zones in which the interaction of light water and seabed produces distinctive physical and chemical conditions. Other shelves at higher latitudes are cooler and may receive less intense solar input, yet still share the general character of shallow land-influenced seas. In many regions, the shelves are not simple flat platforms, but are dissected by channels and punctuated by local highs related to older structural elements or to the build-up of solid frameworks through biological and sedimentary processes. Where tectonic margins are passive and subsiding, these shelves can be very wide, extending far from the present shoreline into what would on a lower sea level world be part of the exposed continent. Because sea level is high, much of the continental interior along these passive margins is submerged beneath epicontinental seas. An epicontinental sea is a shallow, often gently sloping body of marine water that lies directly over continental crust far from the continental edge. In the Devonian world, such seas are prominent on parts of Euramerica and in several basins on Gondwana. They can cover areas comparable in size to modern large countries, or even groups of countries with depths that allow waves and currents to interact readily with the seabed. Within these seas, salinity and temperature can vary with distance from the open ocean and with the balance between marine water, inflow river discharge, and evaporation. Some parts behave much like broad continental shelves open to the ocean, while others become more restricted basins with limited exchange where stratification of the water column and variable oxygen conditions are possible. The boundaries between open shelf epicontinental sea and deeper ocean are not sharp lines but gradational zones whose positions may shift over geological time as sea level and sediment supply change. Where the sea meets the land, coastal environments appear in a wide range of forms depending on local relief tidal range wave energy and sediment input. Low-gradient continental margins with ample sediment delivery from rivers tend to host broad coastal plains, deltas, barrier island systems, tidal flats and estuaries. On such coasts, rivers bring sand, silt and clay from interior highlands to the sea, constructing deltas that protrude seaward and form networks of distributary channels and interdistributary bays. Barrier islands and spits may grow along strike where waves rework sediment into elongated bodies that lie just offshore, sheltering quieter lagoons on their landward sides. Tidal flats occupy low-lying areas that are flooded and exposed on daily and fortnightly cycles, with alternating layers of sand and mud that record the passage of individual tides and storms. Estuaries where river water and seawater mix form where valleys are drowned by rising sea level, or where the balance of freshwater inflow and tidal mixing favours a graded salinity structure upstream from the open sea. On more rugged or tectonically active coasts, narrow shelves and steeper slopes concentrate wave energy onto rocky headlands and cliffs with small embayments, pocket beaches and submarine canyons cut into the margin. In those settings, coarse sediments such as gravel and sand may move along shore under the influence of waves while only thin veneers of finer material accumulate in protected pockets. The vertical dimension of the landscape is controlled by the interaction of tectonic uplift and subsidence with erosion and sediment deposition. Some regions of Euramerica already contain significant uplands and mountain belts formed during earlier collisions, and these higher areas act as sources of sediment and as climatic modifiers at regional scales. From these uplands, rivers descend through foothills and across Piedmont zones before reaching lowland plains and deltas. Over parts of Gondwana, large interior basins collect sediment shed from surrounding highlands, and their surface expression can range from shallow lakes and wetlands to broad, gently sloping plains that may be periodically flooded. Other sectors of the continents remain relatively low relief, but stand above sea level, providing platforms on which terrestrial environments develop. In terms of climate, many coastal and lowland areas in low to middle latitudes experience warm and humid conditions that support the spread of surface water and vegetation, while some interior or rain shadow regions are more seasonally dry or semi-arid. However, the present layer treats these climatic influences only insofar as they help define whether a surface region is dominantly marine coastal or terrestrial. On the emergent land surface, environments include river valleys, floodplains, low uplands and early forested landscapes. River valleys are zones where flowing water incises and reworks sediment, transporting material from high to low ground. Floodplains are broad areas adjacent to the river channels that are periodically inundated during high flows, receiving layers of fine sediment. Low uplands, in contrast, remain above the reach of most floods, and may develop thinner sediment covers or expose bedrock at the surface. In some parts of the continents, especially at low latitudes and in regions with adequate moisture, vascular plants have spread across these surfaces, leading to the development of early forest patches and more continuous cover in certain areas. In others, plant cover remains sparse or patchy, and the land surface continues to be dominated by physical weathering and by the direct action of wind and water. Upland regions with steeper slopes can be prone to more rapid erosion, generating coarse sediment that is carried downslope and deposited in alluvial fans or channel belts, while low-gradient plains encourage the deposition of finer material and the development of more stable surfaces. Beyond the emergent continental surfaces lie upland regions where the combination of tectonic elevation and climate may maintain cooler conditions, and where snow and ice appear seasonally on high peaks, even in a largely greenhouse world. These high areas are limited in spatial extent compared with the broad lowlands and shallow seas, but contribute significant amounts of sediment and dissolved ions to the surface system through weathering and erosion. Across all these domains, the key characteristic of Devonian surface environments is the prominence of shallow water and low-lying regions due to high sea levels and the specific arrangement of continents. Deep oceans occupy most of the planetary area, but the zones of interaction between land and sea, including continental shelves, epicontinental seas and coastal plains, are especially extensive and structurally complex. Land areas are large enough to host diverse terrestrial settings, from low coastal plains through river networks and early forested uplands to higher mountain belts, yet are configured in such a way that oceans and shallow seas remain dominant in the global surface budget. These surface environments form the physical template on which ocean ecosystems, coastal transitions, terrestrial biotas, and geochemical cycles operate in the Devonian world. In the Devonian interval around 400 million years ago, the oceans support complex ecosystems that occupy open waters, continental shelves, reef systems, and deeper basins, and these communities include many of the most diverse animal assemblages of this world. The physical backdrop already described in earlier layers with high sea levels and extensive shallow seas means that a large share of the biologically active ocean lies in relatively warm, well-lit water above continental crust. In these regions, sunlight penetrates through the upper part of the water column and allows photosynthetic organisms to form the primary level of food production. Microscopic algae and cyanobacteria inhabit this sunlit layer suspended in the water as plankton. The exact taxonomic composition of this plankton differs from that of the modern world, because some major groups that dominate later geological intervals are not yet prominent, but the functional role is comparable. They take up dissolved carbon dioxide and nutrients and convert them into organic matter using light energy. Small zooplankton, including tiny crustaceans and the larval stages of larger invertebrates, graze on this phytoplankton and themselves become food for larger animals. This pelagic web extends from the surface down to depths, where light becomes too weak for photosynthesis, and its components drift with currents rather than remaining attached to the seabed. Below and within this layer, continental shelves and platforms host rich benthic communities that are tied to the sea floor. In warm, clear, shallow waters, especially on low-latitude shelves and epicontinental seas, reef systems built by corals and stromatoporoids are prominent. Tabulate and rugose corals, together with sponge-like stromatoporoids, secrete calcium carbonate skeletons that accumulate over time into rigid frameworks. These frameworks create three-dimensional structures with cavities, crests, and slopes that provide many different microhabitats for other organisms. Between and upon the skeletal elements live brachiopods, crinoids, bryozoans, mollusks, and various small arthropods, each attached resting or moving among the surfaces. Many of these animals are filter feeders that draw suspended particles from the water, while others graze on films of algae or scavenge organic material. The reefs thus act not only as accumulations of skeletal material, but also as centres of biodiversity and as local modifiers of currents and wave energy. Surrounding the reef cores there are flanking zones of carbonate sand and mud, produced by the breakdown of skeletons and by the activities of organisms that bore into or graze on hard substrates. On shelves and in epicontinental seas where conditions are less favourable for reef building, other benthic assemblages dominate. Soft sea floors covered in sand silt or mud support communities of brachiopods, bivalves, gastropods, trilobites, echinoderms and burrowing worms. Brachiopods anchor themselves to the substrate or rest upon it, filtering food from the passing water. Crinoids extend their stalked bodies into the flow to intercept particles, while brittle stars and other echinoderms move across the sediment surface. Trilobites, though past their peak diversity compared with earlier times, still occupy roles as deposit feeders, scavengers, and in some cases predators. Many animals burrow into the sediment, creating tunnels and chambers that oxygenate the upper layers of the seabed and mix organic matter into the substrate. The resulting bioturbation alters the texture of the sediment and influences how it records the passage of time. Higher in the water column above these benthic communities, nectonic animals capable of active swimming move through the shelf seas and open oceans. Straight and coiled cephalopods, including ammonoids and nautiloid relatives, are abundant and diverse. Their chambered shells allow them to regulate buoyancy, and muscular bodies with tentacles give them the ability to pursue prey. Armored-jawed fishes, known as placoderms, along with early sharks and bony fishes, occupy many of the higher trophic levels. Some placoderms attain large body sizes and have heavily armoured heads and shoulders with powerful jaws, while others are smaller and adapted to different feeding strategies. Early cartilaginous fishes and lobe-finned and ray-finned bony fishes fill a wide range of ecological roles, from mid-water pursuit of smaller fish and cephalopods to feeding on invertebrates near the seafloor. In this layered structure, energy flows from microscopic producers through small grazers, then to larger predators and scavengers, with carcasses and waste products eventually sinking to the seabed where they are broken down by decomposers. The structure of ocean ecosystems varies between different parts of the marine realm. In the open ocean, far from land, nutrients in the surface layer can become depleted as phytoplankton use them faster than they are resupplied from below. In such regions, productivity may be limited by the rate at which deeper, nutrient-rich waters are mixed upward by current seasonal overturn or wind-driven upwelling. The planktonic communities there are adapted to these relatively dilute nutrient conditions, and large, complex benthic communities are less developed because deep sea floors receive only a modest downward flux of organic material. On continental shelves and in epicontinental seas, in contrast, the proximity of land and the shallowness of the water tend to increase nutrient availability. Rivers deliver dissolved ions and fine sediments from weathering on land, including phosphorus and other biologically important elements. Wave and tidal stirring can resuspend nutrients from the seabed into the water column. As a result, these shallow seas often support higher primary productivity and a greater density and diversity of organisms, especially where clear water and warm temperatures coincide. Reefs flourish under such conditions, but even where reefs are absent, dense shell beds and mixed assemblages of benthic animals can form. The oxygen content of the water is another key factor that shapes Devonian ocean ecosystems. In well-mixed shallow seas, the water column is typically oxygenated from surface to seabed, supporting a wide range of aerobic organisms. However, in deeper basins and in some restricted epicontinental settings, the balance between oxygen supply and consumption can lead to low oxygen or even anoxic conditions near the bottom. When stratification prevents efficient mixing between surface and deep waters, or when high rates of organic matter deposition drive intense bacterial respiration at depth, bottom waters may become depleted in oxygen. In such settings, many typical benthic animals cannot survive, and the seafloor hosts only specialized or sparse communities, or remains nearly barren of macrofauna. Fine, dark muds rich in organic matter can accumulate under these conditions, and they belong to the set of sediments that record oxygen-poor environments in this time window. Even within well-oxygenated areas, gradients of light temperature and substrate type divide ecosystems into zones. The upper photic zone hosts most photosynthetic life, While below it in dimmer waters, animals rely on organic matter transported from above. On shallower substrates where waves and currents are strong, organisms are adapted to frequent disturbance and to shifting sand and gravel, whereas in quieter, muddier settings, burrowing and tube-building forms dominate. Along the flanks of continents where shelf breaks give way to steeper slopes, communities change again with fewer reef builders and more organisms adapted to life on inclined, often fine-grained substrates. Across all these regions, organisms interact not only through feeding, but also through competition for space, through mutual influences on water clarity and chemistry, and through the physical modification of their habitats. Reef builders create structures that alter local flow patterns and light environments. Burrowers and shelly animals change the nature of the sediment column. Plankton blooms may temporarily reduce water clarity or alter the balance of chemical species. Over long spans of time, these biological processes feed back into the physical evolution of the marine environment by constructing carbonate platforms generating sediment and influencing the chemistry of the oceans. From the viewpoint of this Devonian slice, ocean ecosystems are characterized by a strong emphasis on invertebrate-dominated benthic communities, on shelves and reefs, an active pelagic realm populated by cephalopods and early fishes, and significant spatial variation linked to depth distance from land and the structure of ocean basins, all operating within a generally warm high sea level world that provides extensive shallow marine habitat. In the Devonian interval around 400 million years ago, the narrow zones where land and sea meet form transitional environments that connect terrestrial surfaces, rivers, and shallow marine waters. These coastal and shallow water settings include beaches, barrier systems, tidal flats, lagoons, estuaries, and coastal wetlands, each defined by a particular combination of wave and tidal energy, sediment supply, water depth and salinity. They act as interfaces through which sediment dissolved substances and organic matter pass from continents to oceans and from oceans back onto continents. A useful way to describe them at this layer is to follow the path of water and sediment as it moves from interior catchments, down river channels across lowland plains and into marginal marine basins. Rivers draining uplands and low plateaus in Euramerica and Gondwana transport a mixture of dissolved ions and solid particles produced by weathering of bedrock and soils. Where vegetation is sparse, runoff can be rapid, and sediment loads dominated by coarse material and unstable fine particles. Where early forests and ground cover are present, roots and organic litter increase the stability of soil's slow overland flow and change the balance between dissolved and particulate export. In all cases, river channels eventually reach coastal lowlands where gradients decrease and flow begins to split into multiple distributaries, especially where large volumes of sediment are supplied. At such mouths, deltas form as sediment accumulates faster than it can be dispersed by waves and tides. Devonian deltas entering epicontinental seas or open shelves consist of networks of channels separated by bars and interdistributary bays. Sand is generally deposited in channel belts and mouth bars, while finer silt and clay settle in quieter bays and floodplains. The geometry of a delta reflects the relative influence of river discharge wave reworking and tidal currents. Some coastlines in this interval are more strongly shaped by waves which smooth the shoreline, redistribute sand alongshore, and build barrier islands and spits that parallel the coast. In such wave-influenced settings, rivers may deliver their loads into shore-face zones where longshore currents spread sediment laterally, and lagoons or back barrier bays develop on the landward side of the barriers. Other coastlines experience strong tides due to basin geometry and the positions of land masses and the moon. Their tidal ranges are greater, and intertidal flats, tidal channels, and sandbars dominate the coastal morphology. In mixed energy settings, both waves and tides act together to create complex mosaics of bars, channels, and flats. Lagoons in the Devonian coastal realm are shallow, restricted bodies of water lying landward of barrier islands or within partially enclosed embayments. Their salinity can vary from nearly marine to brackish, or even more strongly modified depending on the balance between seawater exchange through inlets, river inflow, direct precipitation, and evaporation. In some cases, lagoons communicate freely with the open sea through multiple tidal inlets, allowing regular flushing and maintaining salinities close to marine values. In other cases, especially where barriers are more continuous, or where tidal ranges are modest, exchange is weaker, and water residence times are longer. Under these conditions, stratification of the water column and variable oxygen levels can develop, particularly if high primary productivity or strong inputs of organic matter from land lead to elevated rates of decomposition. Sediments in lagoons are typically fine-grained muds, often rich in organic matter, interlayered with thin sand beds introduced by storms or channel migration. Fossil evidence from lagoonal deposits in this time window shows assemblages of mollusks, brachiopods, and other invertebrates that tolerate variable salinity, although the specific taxonomic mix differs from that of modern settings. Tidal flats occur where broad expanses of low-lying coastal surface are regularly flooded and exposed by the rise and fall of the tide. In the Devonian world, tidal flats may fringe barrier islands, line estuarine channels, or extend across embayments on wide shelves. On sandy flats, ripples and larger bed forms migrate under the influence of tidal currents, leaving characteristic cross-stratification in the resulting deposits. On muddier flats, cohesive sediment accumulates in thin layers, and burrowing organisms rework the uppermost horizons, producing bioturbation structures. In low-gradient areas with mixed sand and mud, tidal creeks and small channels dissect the flats, focusing currents and transporting sediment between the flats and deeper channels. The distribution of plant cover influences these flats by stabilizing some surfaces and promoting the development of more permanent marsh-like conditions along certain belts, although fully developed densely vegetated salt marshes of the kind familiar from later periods are not yet widespread. Estuaries represent another important transitional environment. They occupy drowned river valleys, or broad lowlands where fresh water from rivers mixes with seawater under the influence of tides. In the Devonian interval, high sea levels favour the creation of such settings, because rising water floods lower reaches of valleys and low coastal plains. Within an estuary, salinity typically increases from the riverhead toward the mouth, and the vertical structure of salinity can range from well-mixed to strongly stratified depending on the balance between river inflow and tidal stirring. Suspended sediment concentrations often peak in intermediate zones where currents decelerate and particles flocculate, forming turbidity maxima. The resulting deposits are a mixture of sand and mud, arranged into bars, point bar-like features and channel fills. Estuaries also serve as conduits for nutrients transporting dissolved and particulate forms of nitrogen, phosphorus, and trace metals from land to sea. In partially enclosed embayments and protected estuarine reaches, early land plants that tolerate occasional flooding can colonize shorelines and low banks, especially in regions where freshwater influence is strong. Their roots help bind sediment, reduce erosion, and promote the accretion of fine material, thereby gradually altering channel positions and bank geometries. Coastal wetlands broadly defined include these vegetated lowlands subject to periodic inundation by marine or brackish waters and by river floods. In the Devonian setting, they are spatially patchy and strongly controlled by topography and plant distribution. Where early forests extend close to the coast, riparian zones and low terraces may host plant communities that experience fluctuating water tables. In lower latitude, humid sectors, repeated flooding deposits thin layers of fine sediment among roots and trunks, encouraging the build-up of organic-rich soils. In contrast, in more arid or seasonally dry coastal zones, wetlands may be limited to narrow belts along channels and springs. The interaction between plant cover and hydrology in these zones influences the chemistry of both soil and shallow groundwater. As roots take up water and nutrients, and as plant litter decays, concentrations of dissolved organic compounds bicarbonate and various ions change, and these modified waters can enter nearby estuaries, lagoons, and nearshore seas. Across all these coastal environments, the role of sediment is central. On land, physical and chemical weathering break down rock into grains and solutes. In catchments with well-developed soils and vegetation, chemical weathering of silicate and carbonate minerals releases cations and bicarbonate that are carried in solution by rivers. In less vegetated areas, physical erosion supplies larger volumes of sand and gravel. Once at the coast, these sediments are sorted by waves, tides, and currents concentrated into beaches and bars spread across tidal flats or carried into deeper water. Fine particles may remain in suspension for long distances before settling in quieter environments such as distal shelves, lagoon interiors, or deeper basins. The balance between sediment supply from land and the capacity of coastal processes to redistribute and remove material determines whether shorelines per grade remain stable or retreat. In areas with strong plant influence on erosion and runoff, sediment yields may be reduced compared with bare ground, but the character of the sediment may change with a higher proportion of fine material produced through enhanced chemical weathering and soil formation. Nutrient dynamics in these transitional settings reflect the combined influence of terrestrial inputs in situ production and exchange with the open ocean. Weathering of rocks and soils supplies dissolved phosphorus, nitrogen in various forms and trace elements. Decomposition of plant litter in soils and wetlands adds dissolved organic carbon and nutrients. Within estuaries and lagoons, phytoplankton and benthic microalgae take up these nutrients, while microbial communities remineralize organic matter, returning some nutrients to dissolved form. Part of the nutrient load is exported seaward, supporting productivity on shelves and in nearshore waters. Part is retained through burial of organic-rich muds in lagoons, tidal flats, and coastal wetlands, linking these environments to longer-term biogeochemical cycles. Because the spread of land plants is an ongoing process in this interval, the strength and pattern of their influence vary geographically. In regions where forests are dense and soils thick, chemical weathering rates and associated cation and bicarbonate fluxes to the ocean may be elevated, whereas in areas where plants are sparse, physical erosion and direct runoff dominate. The resulting spatial variability in sediment and nutrient delivery contributes to differences among Devonian coastal systems, even under a broadly similar greenhouse climate. From the perspective of the outer to inner path, these transitional zones can therefore be understood as dynamic links that transmit water sediment and dissolved substances between continents and oceans, while being progressively modified by the emergence and expansion of vascular plants and early forest ecosystems on land. On the continents of the Devonian world around 400 million years ago, landscapes are undergoing a marked transition from surfaces dominated mainly by bare rock, thin weathering mantles and low simple plants, to terrains in which vascular vegetation forms extensive cover, and in some regions true forests. Lowlands, coastal plains and interior basins near humid belts host the most continuous plant cover, while uplands and drier interiors carry more discontinuous assemblages. Across many equatorial and low-latitude sectors of Euramerica and along suitable margins of Gondwana, the land surface is no longer an open expanse of rock and sediment alone. Instead, it is structured by plant communities that occupy floodplains, river margins, gentle slopes, and some upland plateaus. At the simplest end of this vegetated spectrum, there are areas where low vascular plants only a few tens of centimeters tall form dense mats or small thickets on damp ground. These early tracheophytes possess conducting tissues that transport water and dissolve nutrients from the substrate to photosynthetic tissues, above allowing them to grow taller and occupy drier microsites than non-vascular ancestors. Many lack true leaves in the modern sense and present instead branching axes with small outgrowths, but at this scale they nevertheless transform the appearance and roughness of the land surface. Their presence reduces direct raindrop impact on bare sediment, slows overland flow, and introduces organic matter into the developing soils. In somewhat deeper and more stable substrates, larger vascular plants establish. Lycophytes, which are relatives of later club mosses, produce upright stems with small simple leaves and rooting structures that penetrate the substrate to depths greater than those of earlier plants. Some members of this group attain heights of several meters, forming stands that can be regarded as protoforests in certain localities. Other clades, including ancestors of ferns and horsetail-like plants, add to the vertical structure with frond-bearing stems and jointed ribbed axes. Their fronds intercept light and generate distinctive patterns of shade on the ground, while their stems and roots interact with sediment and shallow groundwater. Over time, the accumulation and decomposition of their tissues contribute to the build-up of organic horizons and to the development of more complex soil profiles. Among the most significant components of these landscapes are tree-sized plants such as Archaeopteris and related progymnosperms. These organisms have woody trunks that can reach heights of several to many meters and diameters large enough to provide substantial mechanical support. Branch systems radiate outward and upward, bearing flattened leaf-like structures that greatly increase the photosynthetic surface area compared with earlier plants. Their rooting systems extend both downward and laterally stabilizing the substrate and exploring significant soil volumes for water and nutrients. Where such trees become locally abundant, they form forest stands with recognizable canopy layers. In these stands, the upper canopy intercepts a large fraction of incoming sunlight, lowering light levels at the ground surface and creating marked vertical gradients in temperature, humidity, and wind speed. Beneath the canopy, intermediate layers may be composed of smaller trees, large shrubs, and tall herbaceous plants, while the ground layer supports low vascular plants, bryophyte-like forms, and developing leaf litter. This stratification introduces a level of structural complexity to Devonian landscapes that is absent in earlier times. On floodplains and low terraces adjacent to rivers, forests, and other plant communities interact closely with hydrological processes. Tree roots reinforce banks and lower slopes, reducing the frequency and magnitude of channel migration, compared with unvegetated systems, and promoting the formation of more stable meander belts in some settings. Woody debris, including fallen trunks and branches, can obstruct flow, locally creating pools and backwaters and influencing sediment deposition patterns. During flood events, vegetated floodplains trap suspended sediment, building up overbank deposits that bury and preserve root stumps and fallen material. Over many such events, these processes help construct layered sequences of mud, silt, and fine sand interbedded with organic rich horizons that represent former soil surfaces and forest floors. In low-lying regions with high water tables, repeated flooding and slow decomposition can lead to local accumulations of organic matter thicker than typical surface litter, although extensive, laterally continuous peat deposits of the kind known from later periods are not yet widespread. On gentle slopes and upland surfaces, the presence of vegetative cover modifies both physical and chemical weathering. Roots penetrate cracks in bedrock and regolith, prizing apart grains and enhancing the ingress of water. Organic acids produced by roots and associated microbial communities accelerate the dissolution of minerals, releasing cations and silica into solution and leaving behind more stable components such as certain clays and oxides. Over time, these processes deepen the weathered mantle and create more differentiated soil horizons, with upper layers enriched in organic matter and lower layers altered by leaching and secondary mineral formation. The resulting soils support higher plant biomass and provide a more buffered environment for nutrient cycling than the thin, poorly developed regoliths that preceded them. At the scale of topography, vegetated hill slopes respond differently to rainfall and runoff than bare slopes. In forested and densely vegetated areas, interception of rainfall by canopies and absorption by litter reduce the kinetic energy of water at the ground surface, lowering erosion rates for a given rainfall intensity. Greater infiltration capacities allow more water to enter the subsurface, sustaining base flow in streams and moderating peak discharges. In contrast, in sparsely vegetated or recently disturbed areas, intense storms can still produce rapid runoff, sheet wash and gullying. The spatial pattern of forests, open woodland, scrub and nearly bare ground therefore exerts a strong control on the distribution of erosional and depositional environments, and hence on the development of landforms. In some sectors of Euramerica and Gondwana, particularly near the equator, where temperatures are warm and precipitation is ample, forest and woodland cover may form near continuous belts along lowlands and lower slopes. Farther into the interiors of large continents, or in regions where circulation patterns limit moisture supply, plant cover becomes patchier, confined to river corridors, springs and depressions where groundwater is accessible. At higher latitudes or altitudes, cooler conditions and seasonal constraints on growth impose their own limits, and vegetation may be dominated by lower stature forms adapted to shorter growing seasons and cooler temperatures. Across this spectrum, the common feature is that vascular plants of various sizes now occupy a large fraction of suitable land surfaces, so that bare rock and unconsolidated sediment are no longer the default ground cover outside the driest or most recently disturbed zones. The spread of early forests and associated plant communities also alters fluxes of gases and water vapor between land and atmosphere. Through transpiration, plants return significant quantities of water to the air, influencing humidity profiles and potentially feeding back on cloud formation and precipitation at regional scales. Through photosynthesis, they assimilate carbon dioxide and release oxygen, while respiration by plants and soil organisms returns some carbon dioxide to the atmosphere. Over long time scales, the balance between primary production decomposition and burial of organic matter determines whether vegetated landscapes act as net sources or sinks of atmospheric carbon. Within the narrower time window around 400 million years ago, these processes are actively reshaping the coupling between land surfaces and the atmosphere, even though their integrated effects on global gas inventories are evaluated over longer intervals. Fire is a potential process in vegetated landscapes that depends on both fuel availability and oxygen concentration. Geochemical and sedimentary evidence indicates that wildfires are present in at least parts of the Devonian, implying that atmospheric oxygen exceeds the threshold necessary to sustain combustion in dry plant matter. However, the precise frequency, geographic distribution, and ecological significance of fire in this specific interval are not well constrained. It is therefore appropriate to acknowledge that some landscapes may experience occasional burning, which influences fuel loads, plant community composition, and soil properties, while recognizing that current data do not support a detailed reconstruction of fire regimes comparable to those available for later periods. Overall, the combination of early forests' diverse vascular plant assemblages and their associated soils produces Devonian landscapes that are topographically and structurally more complex than those of earlier Paleozoic times. River valleys, floodplains, low uplands, and some higher plateaus now host tree-dominated stands, open woodlands, scrub and herbaceous covers that interact with hydrology, erosion and weathering. In humid regions, continuous or nearly continuous vegetation stabilizes large areas, while in drier or cooler settings, patchy plant cover and more frequent exposure of bare ground maintain higher erosion rates. These patterns generate a mosaic of landforms and substrates, from stable soil-covered surfaces under forest canopies to actively reworked sediment bodies along rivers and on sparsely vegetated slopes. Within this framework, the physical template is in place for terrestrial animal communities, later soil processes and microscale habitats. But at this layer, the emphasis remains on the organisation and effects of early forests and plant-dominated landscapes that characterise much of Earth's emergent surface in this Devonian window. Within the vegetated landscapes of the Devonian interval around 400 million years ago, terrestrial ecosystems consist of plant-dominated surfaces that are occupied and modified by invertebrate animals, especially arthropods. These ecosystems are spatially patchy and vary according to local climate, substrate and plant structure, but across many lowland and low upland regions there is a recurring pattern of forest stands, woodland, scrub, and more open ground, each with its own set of arthropod assemblages. The animals present are inferred from both body fossils and trace fossils, with particularly detailed information coming from sites where plants, soils and animals are preserved together in fine-grained deposits. At the broader scale, one can distinguish communities associated with the forest floor and litter layer, with the surfaces of stems and leaves with decaying wood and plant debris, and with shallow subsurface zones in the upper soil. On the forest floor beneath stands of tree-sized plants such as Archaeopteris, and within dense thickets of smaller vascular plants, thick accumulations of leaf-like organ stems and reproductive structures form a heterogeneous litter layer. In this layer, millipede-like myriapods and related forms move among the debris. Their elongated bodies, many segments and numerous pairs of legs allow them to navigate through narrow spaces and over irregular surfaces. Their mouthparts and gut contents in fossil relatives from this and nearby intervals suggest feeding on decaying plant material and associated microorganisms rather than on living intact tissues. By fragmenting litter and mixing it with mineral grains, they accelerate the incorporation of organic matter into the upper soil, and their burrow systems increase porosity and influence the distribution of moisture and gases. Alongside these detritivores, there are arthropods with morphologies consistent with predatory or scavenging habits. Early arachnids, including spider-like forms and scorpion lineages, occupy the litter layer and the immediate ground surface. The fossil record indicates the presence of segmented bodies, jointed limbs and mouth parts, adapted for grasping or piercing, supported by respiratory structures suited to life in air. Some arachnids likely wait near burrow entrances or sheltered points, capturing smaller arthropods that pass within reach, while others may be more mobile hunters. Their activity, together with that of other small predators, imposes a control on the abundance and spatial distribution of smaller detritivores and microherbivores. The ground surface and low vegetation also host early insects and insect-like wingless hexapods. Fossil evidence from this interval and from slightly younger strata records, small-bodied forms with mouth parts adapted either for chewing or for sucking, indicating a range of diets that may include fungal material, algae, decaying organic matter, and in some cases living plant or microbe-rich films. Many of these animals are likely to remain close to moist microhabitats such as the undersides of leaves, the bases of stems and the interfaces between litter and soil, because their small size and cuticular properties make them sensitive to desiccation. Their movements, feeding and waste production further modify the microstructure and chemistry of the litter and surface soil. On stems, fronds and branches of taller plants, there is a three-dimensional network of potential habitats. Small arthropods can occupy the surfaces of leaves, nodes along stems, and the intersections between branches. Some may feed directly on plant tissues by scraping or piercing, leaving small marks and scars that are preserved in some fossil plant assemblages. Others may graze on epiphytic films of algae, fungi, and bacteria. The density and distribution of these organisms depend on the architecture of the plants, the degree of shading, and the local microclimate. For example, densely foliated crowns produce shaded, more humid microenvironments in their interiors, favouring forms that require stable moisture, whereas outer surfaces exposed to more direct airflow and solar radiation are occupied by forms more tolerant of fluctuations. Arthropods associated with decaying wood represent another important component of these ecosystems. As tree-sized plants age, die, and fall, their trunks and larger branches become substrates for colonization by fungi, bacteria, and invertebrates. Early wood-boring arthropods, including certain insects and their relatives, penetrate the outer tissues and move through the decaying material. Their tunnels increase the surface area exposed to microbial decomposers and alter the mechanical properties of the wood. Over time, the combination of microbial breakdown and invertebrate activity causes logs to disintegrate into smaller fragments that contribute to the litter and soil matrix. The rate and pattern of this process influence nutrient release back into the ecosystem and the structure of the ground layer. In addition to these ground and plant-associated assemblages, shallow subsurface environments host their own arthropod communities. In the upper soil horizons, small arthropods occupy pore spaces and microvoids, moving among mineral grains, root hairs, and organic fragments. Their activities include feeding on microorganisms, fine organic particles, and each other, while their movement and burrowing help maintain soil structure and facilitate gas and water exchange between the surface and deeper layers. The depth to which oxygen penetrates depends on soil texture, moisture content, and biological activity, and most animals remain within the zone that retains both adequate oxygen and sufficient moisture. In drier or more compacted soils, these zones may be restricted to narrow bands along roots or near fractures, whereas in looser, more organic, rich soils they can be more extensive. The composition of terrestrial arthropod communities varies between different landscape positions. On well-drained ridges and upland slopes with thinner soils and more exposure to wind and radiation, plant cover is less continuous, and litter layers are thinner, so arthropod assemblages may be dominated by species adapted to greater fluctuations in temperature and moisture. In valley bottoms, floodplains and depressions where soils remain moist for longer periods, litter accumulation is greater and both plant and animal biomass can be higher. Periodic flooding in these areas imposes disturbances that some arthropods can survive by retreating into soil pores or by recolonizing from nearby refuges once waters recede. On coastal lowlands and near the margins of lakes and rivers, terrestrial and aquatic or amphibious environments intersect. Here, some arthropods spend different life stages in different media, for example, laying eggs in moist soils or near water bodies, and having mobile stages that move over land surface. Others forage along shorelines, exploiting stranded organic material and prey that move between water and land. These marginal settings are sensitive to changes in water level sedimentation and plant cover, and thus host communities that may change on shorter timescales than those of interior forests. Throughout these ecosystems, the physiology of arthropods imposes constraints that shape their distribution. Their external skeletons provide mechanical support and limit direct water loss, but gas exchange through tracheal systems or analogous structures requires contact with air, and many forms cannot tolerate prolonged immersion or extreme dryness. Consequently, habitats that combine air access with adequate humidity, such as soil surface under litter, protected crevices in bark and dense ground vegetation, tend to support higher densities and diversity. In open, fully exposed surfaces, arthropod activity is more restricted to favourable times of day or to periods following rainfall. The fossil record for terrestrial arthropods in this interval is incomplete, and bias toward environments where rapid burial and fine-grained sedimentation occur, such as volcanic ash deposits lake margins and certain floodplain settings. As a result, not all components of these ecosystems are equally visible in the geological record, and some inferred interactions remain generalized. However, the combination of body fossils, trackways, burrow structures, and damage patterns on plant remains supports a picture of Devonian terrestrial ecosystems in which arthropods already occupy multiple trophic positions. They function as decomposers, microherbivores, predators and scavengers linked by movement of energy and matter from plant production and microbial processing through invertebrate food webs and back into soils and sediments. From the perspective of the larger Devonian world, these terrestrial arthropod communities represent the primary macroscopic animal component of land ecosystems. Vertebrate use of land surfaces is limited, and not yet a dominant factor in structuring these environments according to current evidence, so the main animal interactions with plant soils and detritus are mediated by arthropods and other invertebrates. Their presence adds a dynamic biological layer to the early forests and vegetated landscapes described, previously influencing the rates and pathways of decomposition, nutrient cycling, and soil formation, and contributing to the diversification of habitats within Devonian continental interiors and along lowland plains. In the Devonian interval around 400 million years ago, shallow freshwater and marginal habitats occupy low-lying parts of the continents and form a set of environments in which processes from land and sea intersect. These habitats include river channels, associated floodplains, small to moderate-sized lakes, ephemeral ponds and wetlands that develop in depressions and along the margins of water bodies. They are supplied by precipitation falling on vegetated catchments, by groundwater discharge, and in some coastal regions by mixtures of freshwater and brackish water, where tidal influence reaches inland. Their physical and chemical conditions are controlled by climate topography, the extent and type of plant cover, and the nature of the underlying rocks and soils. In humid belts of Euramerica and suitable sectors of Gondwana river systems drain uplands and plateaus and flow toward epicontinental seas and open shelves. Headwater streams arise on slopes and in upland hollows, often with relatively steep gradients and coarse bed material. As they descend into lower relief terrain, channels widen and gradients decrease, and flow becomes more strongly influenced by bankful events that shape meanders, bars, and floodplains. Vegetation on valley sides and floodplains, including stands of tree-sized plants and other vascular flora, interacts with these channels by binding banks, contributing woody debris and regulating runoff and sediment supply. As a result, many lowland rivers at this interval display patterns of meandering or anabranching channels separated by vegetated islands and bars, even though local variability remains high and some reaches retain more braided characteristics, where sediment loads are large and vegetation less effective at stabilizing bars. The water in these rivers carries dissolved ions derived from silicate and carbonate weathering, as well as suspended fine sediment and organic matter from soils and litter. Its chemistry varies along the course, with headwaters reflecting local bedrock and upland soils and downstream reaches integrating broader catchments. In heavily vegetated basins, concentrations of dissolved bicarbonate and certain cations are elevated by enhanced chemical weathering, while dissolved organic carbon from litter decomposition can darken the water and influence its optical properties. Temperature regimes in these rivers are governed by latitude, altitude, season, and shading. Equatorial lowland streams and rivers are generally warm, especially where direct solar radiation reaches the water surface, but forested reaches under continuous canopy experience moderated extremes. Higher latitude or high altitude rivers are cooler, and strong seasonal contrasts in discharge may occur where precipitation patterns are pronounced. Flow regimes range from relatively steady base flows in basins with substantial groundwater storage and thick soils to more flashy patterns in catchments with thin regolith and sparse vegetation. During high-flow events, floodwaters spread across adjacent plains, depositing thin layers of silt and clay, and forming natural levees near channel margins through rapid settling of coarser suspended material. Over many events, these processes build layered floodplain sequences with interbedded soils, plant remains, and animal traces. Lakes and ponds are common components of these freshwater networks. Some occupy tectonic or structural depressions within continental interiors or along active margins, while others form in subsiding basins within lowlands in abandoned channel segments or in closed depressions on floodplains. Their sizes range from small ponds and oxbow lakes only a short distance across to basins extending for tens of kilometres, though the upper size range in this interval is less constrained by direct evidence than by analogy with later times. Many of these lakes are shallow enough that wind-induced mixing can reach the bottom during at least part of the year, preventing permanent stratification. In others, particularly deeper or more sheltered basins, density stratification between warm surface waters and cooler bottom waters may develop seasonally or persist for longer periods, leading to vertical gradients in temperature and oxygen. Inputs of nutrients and organic matter from surrounding vegetation and soils support phytoplankton and attached algal growth in the photic zone, and microbial decomposition in deeper layers consumes oxygen. Where stratification is strong and mixing in frequent bottom waters can become oxygen poor or anoxic, limiting the presence of complex benthic organisms and favouring the preservation of fine organic rich mud. In contrast, well-mixed lakes with continuous oxygenation support more active benthic invertebrate communities and host diverse microhabitats along shorelines. Floodplains adjacent to rivers constitute dynamic marginal habitats that experience alternating phases of inundation and exposure. During floods, water spreads across these plains, fills depressions, and reconnects channels and lakes that may be isolated at lower stages. As floodwaters recede, a network of shallow pools, backwaters, and slowly draining swales remains. In these settings, fine sediments settle, plant litter accumulates, and early soils develop. Root systems of floodplain forests bind the substrate, while trunks and fallen logs create hydraulic roughness that slows water and promotes sediment deposition. Over repeated cycles, the vertical build-up of overbank deposits and soil horizons can raise some floodplain surfaces above the reach of all but the largest floods, while new lower surfaces form closer to active channels. This constant reorganization of channel belts and floodplain topography generates a shifting patchwork of aquatic, semi-aquatic and terrestrial microenvironments within the broader lowland mosaic. Freshwater fauna in these rivers and lakes includes fishes that are members of the same broad groups present in marine settings, but adapted to non-marine conditions, along with invertebrates and microbial communities. Jawed fishes such as placoderms and early bony fishes occupy various positions in these systems. Some species inhabit main channels and larger lakes where they swim in the water column, feed on smaller fishes and invertebrates, and navigate currents and stratified thermal structures. Others prefer quieter backwaters, floodplain lakes and vegetated margins where they can exploit concentrated food resources and avoid strong flow. Morphological features such as robust fins, specific body shapes and specialized jaw structures reflect these ecological roles. For example, forms with broad laterally compressed bodies and fins positioned to provide high maneuverability are well suited to complex obstacle-rich environments such as submerged root networks and woody debris fields, whereas more fusiform bodies favor sustained swimming in open channels. Some freshwater fishes possess anatomical and physiological traits that allow them to tolerate fluctuations in oxygen availability, turbidity, and temperature, including dense networks of blood vessels in certain respiratory surfaces and behaviours that bring them into well-oxygenated surface layers or moving water. Along with fishes, freshwater invertebrates including various crustaceans, worms, mollusks, and insect larvae occupy different parts of these habitats. On or within river and lake bottoms, detritivories feed on deposited organic material and microbial films, while scrapers graze on algae attached to substrates. Predatory invertebrates hunt within the water column and among submerged plants and woody debris. Many insect lineages with aquatic larval stages in later periods have not yet diversified fully in this interval, according to current evidence, but some basal forms likely already exploit freshwater environments, contributing to the complexity of aquatic food webs. At the margins of lakes and streams where water depth decreases gradually, an emergent or semi-emergent vegetation is present. Interactions between aquatic and terrestrial biota are particularly close. Plant stems and roots that extend into shallow water provide attachment sites and refuges for aquatic invertebrates and fishes. Litter falling from overhanging branches and riparian vegetation enters the water supplying organic carbon that is processed by microbial and detritivore communities. Arthropods from adjacent terrestrial ecosystems move into marginal zones to feed on organisms or material concentrated along shorelines, while aquatic organisms may enter saturated soils or damp leaf litter during high water phases. These exchanges create short pathways by which energy and nutrients move between land and water. Water chemistry in these marginal and freshwater systems reflects a balance between local inputs, internal processing, and outputs downstream. In basins underlain by carbonate rocks, dissolved calcium and bicarbonate tend to be higher, and buffering capacity against pH change is greater. In silicate-dominated terrains, dissolved silica and specific cations prevail. Organic acids from plant litter and soils can lower pH in some lakes and streams, particularly where water residence times are long, and exchange with bedrock is limited. Nutrient concentrations depend on rates of weathering soil, development vegetation density and retention processes within wetlands and floodplains. In regions with extensive forest cover and thick soils, significant fractions of nutrients may be retained on land, or in floodplain deposits leading to moderate nutrient levels in rivers and lakes, while in less vegetated or newly weathered areas, higher nutrient pulses may occur during storms and erosion events. Over geological time, the sediments accumulating in these freshwater and marginal environments form distinct parts of the Devonian stratigraphic record. Channel sandstones with cross-bedding and pebble lags record former river courses. Overbank mudstones with root traces, desiccation cracks, and plant fossils mark ancient floodplains. Laminated mudstones rich in organic matter and finely preserved plant and animal remains reflect quiet lake floors. Heterolithic deposits with alternating ripple-marked sands and mud drapes capture the influence of fluctuating flow conditions in backwaters and shallow embayments. These facies provide evidence for the presence and character of shallow freshwater systems and for the communities that occupy them. Within the time window considered here, such environments are widespread enough to create a continuous set of habitats that link interior land surfaces, early forests, and coastal zones. They serve as corridors for the dispersal of aquatic and semi-aquatic organisms, as sinks and sources for sediments and solutes, and as locations where microscale physical and biological processes interact. Taken together, rivers, lakes, and floodplains in the Devonian world form a network of shallow freshwater and marginal habitats that mediate exchanges between continents and seas, host distinctive assemblages of fishes and invertebrates under variable chemical and physical conditions, and generate sedimentary records that document these interactions within the broader context of a warm high sea level planet. In the Devonian interval around 400 million years ago, the vertebrate life of the seas is dominated by a range of jawed and jawless fishes that occupy many ecological roles, from small bottom-associated forms to large active predators. These vertebrates differ in skeletal structure, external armour, fin design and sensory systems, yet all operate within the physical and chemical framework of warm, generally well-oxygenated shelf, seas, epicontinental basins, and open marine waters described in earlier layers. Jawless fishes, descendants of older Paleozoic lineages, remain part of the marine fauna, but no longer constitute the most conspicuous or diverse group. Many of these agnathan forms possess external bony plates or scales around the head and trunk, with simple mouths lacking true jaws, and with paired fins that are reduced or absent. They inhabit benthic or near-bottom environments where they feed by filtering or scraping fine organic material from sediments and hard substrates. Their presence shows that non-jawed vertebrate strategies still function in some niches, but the wider variety and adaptive radiation of jawed fishes mark a key feature of Devonian marine ecosystems. Among the jawed vertebrates, placoderms are particularly prominent. These fishes have heavy dermal armour over the head and shoulder region formed by large bony plates that are jointed to allow movement between head and trunk. The remainder of the body can be less armoured and more flexible, often covered by smaller scales or left relatively lightly protected. Within placoderms, there is considerable diversity in body shape, size and inferred life habits. Some species are relatively small with streamlined bodies suited to active swimming in open water, while others achieve large body sizes with massive cranial armour and heavy jaws. The jaw apparatus in many placoderms includes bone-like plates that function as biting surfaces, allowing them to grasp, crush or cut prey. Muscle attachments on the skull and lower jaw indicate strong bite forces in some forms, consistent with predatory roles directed at other fishes and large invertebrates. Other placoderms show jaw and tooth plate arrangements more suited to crushing shelled prey or to generalist feeding. Their fins, including pectoral and pelvic pairs, provide lift steering and stability, and their tails can range from heterocircle forms that generate both thrust and upward force to more symmetrical shapes. Placoderms occupy habitats across the marine spectrum from nearshore and shallow shelf waters to deeper, more open environments. Another major group consists of early cartilaginous fishes, relatives of modern sharks and rays. These chondrichthyan fishes possess skeletons composed primarily of cartilage rather than ossified bone, although their teeth and dermal denticles are mineralized and preserve well in the fossil record. Their bodies are generally streamlined with heterocircle tails, paired pectoral and pelvic fins and dorsal fins that contribute to stability. Teeth occur in multiple series and can be replaced through life, and different tooth morphologies reflect different feeding strategies. Some forms have narrow-pointed teeth suited to seizing soft-bodied prey, while others possess flatter, crushing teeth, adapted to feeding on hard-shelled invertebrates. The skin is covered with small denticles that reduce drag and may provide protection. Sensory systems inferred from skull structure and comparison with later relatives include well-developed eyes, olfactory capsules, and inner ears, as well as lateral line systems that detect water movement and vibration. These early sharks and related forms occupy mid-water and near-bottom positions in the water column, acting as pursuit predators, ambush hunters and scavengers across a range of shelf and open marine settings. Bony fishes or osteichthyans are also well represented in Devonian seas and can be grouped into lobe-finned and ray-finned forms. Lobe-finned fishes or sarcopterygians possess paired fins, supported by robust fleshy lobes, containing internal bones arranged in patterns that within this interval provide strong support for fin musculature and controlled movement. Their bodies are often deep or elongated depending on the habitat, and they carry cosmoid or similar scales with layered bony and dentine components. Some lobe-finned fishes, such as coelacanth lineages, have lobed fins with distinct jointing that allows complex fin motions, while others, including early dipnoan or lungfish groups, show modifications that permit air breathing through vascularized structures associated with the gut. In the Devonian marine context, these fishes inhabit a range of environments, from offshore waters to nearshore and estuarine zones, where their powerful fins and flexible bodies support maneuvering among obstacles hovering near the seabed, and possibly short excursions into water masses with variable oxygen content. Their jaws carry tooth fields or tooth plates capable of processing a variety of prey, including invertebrates with hard parts. Ray-finned fishes or actinopterygians in this interval are at an earlier stage of diversification, but are present in both marine and freshwater settings. Their paired fins are supported primarily by thin, radiating, bony elements called fin rays, which attach to more limited internal skeletal structures. This arrangement allows fine control of fin shape and orientation for maneuvering, while a more lightly built skeleton reduces mass and may facilitate rapid changes in speed and direction. Early ray-finned fishes typically have gonoid scales, with hard outer layers and overlapping arrangements that provide protection without excessive loss of flexibility. Their jaws show a range of tooth morphologies suited to capturing small prey in the water column or near the bottom. As with other groups, their sensory equipment includes lateral line systems, eyes adapted to the available light levels in their chosen depth ranges, and inner ear structures for balance and sound detection. Jawed fishes also include acanthodians, sometimes called spiny fishes, which are characterized by stout fin spines, relatively small scales and lightly built bodies. Their exact relationships within jawed vertebrates remain a subject of ongoing scientific analysis, but in functional terms they represent small to medium-sized fishes that occupy both plankton feeding and predatory roles. Some acanthodians have numerous small teeth consistent with planktonic or small prey consumption, while others bear larger, more robust teeth. Their fin spines may play roles in stabilization defense against predators or display, and their distribution across marine and freshwater faces shows that they tolerate a variety of salinity and energy regimes. Across these groups, the evolution and refinement of jaws, teeth, and associated musculature have major ecological consequences in Devonian seas. Jaws allow more efficient capture and processing of prey compared with jawless suction or scraping alone, and teeth extend the range of accessible food types. Combined with improved locomotor systems, including more elaborate paired fins and tails, these features enable jawed fishes to exploit open water niches to pursue agile prey and to specialize on particular feeding strategies. Sensory systems, including lateral line canals, visual organs, and inner ear structures, integrate with these morphological features to support detection of prey predators and environmental cues. Vertebrate faunas vary among different marine habitats. On reef fronts and in back reef lagoons, smaller fishes maneuver among coral stromatoporoids and carbonate sands, feeding on invertebrates and plankton, while larger predators patrol the margins and deeper channels. On broader shelves with mixed substrates, benthic feeders move over soft sediments and firm grounds, disturbing in fauna and consuming organisms in and on the sediment. In epicontinental seas, where water depth is modest and the seafloor lies within storm wave base, fishes must cope with episodically strong currents and resuspension of sediment which favour robust swimmers and forms able to seek refuge in deeper channels or in structurally complex bottoms. In deeper outer shelf and upper slope environments, vertebrates track prey that move between the surface and mid-water layers and exploit gradients in light and temperature. In some basins, intervals of low oxygen at depth restrict vertebrate presence in bottom waters, compressing habitable zones toward the surface and influencing vertical distributions. While these conditions may exclude fishes from certain layers near the seabed, they can also concentrate prey and predators in the upper parts of the water column. Over time, the interplay between environmental conditions and vertebrate morphology leads to diversification. Differences in jaw structure, dentition, fin configuration, body proportions, and sensory capabilities correspond to partitioning of resources and to occupation of distinct habitat types. However, it is important to note that the Devonian record remains incomplete, and that the observed diversity reflects both evolutionary reality and preservation biases. Fossil Lagerstätten provide detailed snapshots of communities in particular settings, while more ordinary deposits yield scattered remains that fill in broader patterns. Within the defined time window, the overall picture is that Devonian seas host a wide array of jawed fishes, including heavily armoured placoderms, streamlined sharks, and their relatives, robust lobe-finned forms, and more lightly built ray-finned fishes, along with residual jawless lineages. Together they form the vertebrate component of marine ecosystems integrated with invertebrate-dominated reefs and benthic assemblages, and with pelagic planktonic systems, and they operate within the physical and chemical constraints of a warm, high sea level planet with extensive shallow marine habitats. In the Devonian interval around 400 million years ago, the plants that occupy land surfaces are not only structural components of landscapes, but also complex organisms with specialized tissues, organs, and life cycles that allow them to persist on solid ground, reproduce, and interact with air, water, and substrate. The dominant macroscopic plants are vascular forms, meaning they possess internal conducting tissues that transport water-dissolved minerals and organic products between different parts of the body. These tissues, together with supporting cell types, underpin the organization of roots, stems, leaves, and reproductive structures in ways that distinguish Devonian vegetation from earlier non-vascular assemblages. At the base of this organization are roots and root-like organs that anchor plants and explore the substrate. In many Devonian taxa, true roots with defined root caps, branching axes, and central vascular strands extend downward from stems into soils and weathered rock. They penetrate porous zones, follow fractures, and occupy intergranular spaces where water and dissolved ions are present. The vascular strand within a root typically consists of water-conducting cells, often thick-walled and lignified, arranged in patterns that support both efficient transport and mechanical strength. Surrounding tissues include cortex regions that store carbohydrates and facilitate radial transport of water and solutes toward the center. In some early groups, functionally similar structures called rhizomes or root-bearing stems run horizontally within or just above the substrate, sending down anchoring branches and upward shoots. These organs allow plants to colonize new patches of ground, stabilize sediment, and maintain access to water and nutrients over irregular terrain. Above the substrate, stems provide vertical and horizontal scaffolding for photosynthetic tissues and reproductive organs. Devonian stems display a range of internal anatomies depending on the group. Many possess a central core of water, conducting tissue or xylem surrounded by food conducting tissue or phloem, and an outer cylinder of supporting and protective tissues. In smaller plants, this arrangement forms a simple strand with limited secondary thickening, sufficient to support low to moderate heights. In tree-sized forms, such as Archaeopteris and other progymnosperms, the vascular system undergoes extensive secondary growth. Cells near the margin of the xylem cylinder divide to produce additional layers of water conducting tissue and associated support cells, forming a woody trunk capable of bearing substantial loads and resisting bending stresses. This woody tissue includes tracheids with thick lignified walls and specialized pits for lateral water movement, providing both stiffness and transport capacity. The outer parts of the stem may develop bark-like coverings formed from tissues that protect against desiccation, mechanical damage, and biotic attack. Branching patterns vary among groups from simple dichotomies in small plants to complex hierarchically organized branching systems in tree-sized taxa, where main trunks divide into large lateral branches and then into finer twigs. Leaves or leaf-like organs expand the area available for light interception and gas exchange. In Devonian floras, two broad categories of photosynthetic appendages can be recognized. In some groups, notably lycophytes' leaves are generally small, simple structures bearing a single vascular trace, often described as microphyls. They arise in spiral or other orderly arrangements along stems and present narrow laminae that house chlorophyll-containing tissues. In other groups, including early ferns and progymnosperms, leaves are larger, with more complex vein networks that branch and rebranch within the lamina, sometimes forming compound fronds with multiple segments. These structures, sometimes called megaphylls, allow the development of broad surfaces in which light is intercepted and carbon dioxide is absorbed while water vapor is released through stomata. The internal anatomy of leaves includes an upper and lower epidermis mesophyll regions, with photosynthetic cells and vascular bundles that distribute water and carry away the products of photosynthesis. Stomata, small openings bordered by specialized guard cells, occur on leaf surfaces and regulate gas exchange in response to environmental conditions. Their density and distribution influence rates of transpiration and carbon uptake, and fossil leaf cuticles preserve their positions and morphologies, providing evidence for atmospheric composition and plant physiological strategies. Reproduction in these Devonian vascular plants is based on an alternation of generations between a diploid sporophyte and a haploid gametophyte, a pattern inherited from earlier land plants, but elaborated through new organs and life history strategies. The dominant conspicuous phase in most vascular taxa is the sporophyte, the familiar plant body with root stems and leaves. On this sporophyte, specialized structures called sporangia form and produce spores through meiotic division. Sporangia are located in different positions in different lineages. In some plants they occur singly, or in clusters on the surfaces or tips of ordinary stems and leaves. In others they are grouped into distinct structures such as cones or strobili, where numerous sporangia are borne on modified leaves or axis segments. The arrangement and morphology of these organs influence how spores are produced, protected, and released. Spores themselves are single cells surrounded by resistant walls that can survive periods of unfavorable conditions during dispersal. Their outer layers often bear sculptured patterns that can be diagnostic of particular plant groups and that influence aerodynamic behavior. In many Devonian species, all spores produced by a plant are similar in size and function, a condition called homospory. These spores germinate upon reaching suitable moist substrates, giving rise to small independent gametophyte plants that bear male and female reproductive organs, or in some cases both on the same individual. The gametophytes are typically low thallus, like structures that require liquid water films for sperm motility, linking reproductive success to microhabitats where moisture persists at least seasonally. In some lineages, however, a shift toward heterospory is underway. Heterosporous plants produce two distinct kinds of spores: larger megaspores that give rise to female gametophytes, and smaller microspores that develop into male gametophytes. This differentiation appears in certain Devonian lycophytes and other groups, and represents a structural reorganization of reproductive investment. Megasporangia contain few megaspores, each with more resources, while microsporangia produce many small microspores. The resulting gametophytes may remain within protective tissues associated with the parent sporophyte for part of their development, especially in the case of female forms. These arrangements foreshadow the evolution of seeds, but in this interval remain limited to early stages in which retention and protection of the developing next generation occur only partially and for limited durations. Seed-like structures begin to appear in some lineages where an integument or enveloping tissue surrounds the megasporangium, leaving an opening for pollen entry. Within a single functional megaspore may give rise to a female gametophyte that remains enclosed and nourished. At the Devonian stage considered here, such structures are not yet widespread or fully developed seeds in the modern sense, but they illustrate how modifications of spore-based life cycles can concentrate reproductive investment and improve survival prospects for developing embryos. The relationships between sporophyte and gametophyte generation differ among groups. In homosporous plants, the gametophyte is usually free-living and autotrophic or partially autotrophic, drawing resources directly from the environment. In emerging heterosporous forms, male gametophytes become reduced in size and duration, functioning as carriers of sperm cells that reach the female organs through direct deposition or via transport structures. Female gametophytes become more tightly associated with parent sporophyte tissues, leading to increased protection and potentially greater control over the environment of fertilization and early development. These shifts alter the sensitivity of reproduction to external conditions such as drought and temperature variation. At the cellular level, plant tissues associated with reproduction show specializations that support these functions. Sporangia contain spore mother cells surrounded by layers of nourishing and protective tissue, and dehiscent zones where cell walls weaken to allow release of mature spores. Gamtangia on gametophytes, including structures that produce eggs, and sperm are embedded in tissues that regulate water content and protect developing gametes until conditions favor fertilization. After fertilization, zygotes remain attached to the gametophyte for some period, drawing resources to complete early embryonic development, before emerging as new sporophytes. Beyond reproduction, the internal structure of Devonian plants includes several tissue systems that maintain water balance and mechanical stability. The vascular system with xylem and phloem connects roots, stems and leaves in continuous networks. In roots, xylem strands converge as they approach the tips, while in stems they form rings or more complex patterns that distribute support and transport functions through the organ. In leaves, minor veins connect to larger bundles, ensuring that water reaches photosynthetic cells and that sugars produced in those cells can be exported. Surrounding the vascular system, ground tissues such as parenchyma provide storage and fill spaces, while sclerenchyma and fibers confer rigidity where needed. Epidermal tissues form the outermost layer, often covered with a cuticle, a waxy coating that reduces uncontrolled water loss and offers some protection against pathogens and physical abrasion. Stomatal complexes are embedded in this epidermis, and their regulation of aperture size responds to internal water status and external factors such as light and humidity. These structural and physiological features interact with the external environment in systematic ways. Roots and associated mycorrhizal associations with fungi extend the effective reach of plants into soil pores, enhancing uptake of phosphorus and other nutrients. Leaves and stems adjust their orientation and growth to optimize light capture, while managing mechanical loads from wind and the weight of the plant itself. Woody tissues in trunks and large branches balance the need for vascular capacity with the requirement for resistance to buckling and fracture. The life cycle with alternation of generations and spore-based dispersal allows plants to occupy new substrates as spores travel by air and water, while vegetative growth through rhizomes and branch proliferation consolidates colonies in favorable sites. The combination of these anatomical and life history traits explains how Devonian plants are able to colonize extensive areas of land, maintain coherent populations in variable conditions, and establish the foundational biological structures that later interact with soil's geochemical cycles and microscale life. In this time, window plant bodies and life cycles thus represent integrated solutions to the challenges of living on solid ground, capturing resources from air and substrate, and reproducing across landscapes shaped by both stability and disturbance. In the Devonian interval around 400 million years ago, the chemistry of soils, rivers, and shallow seas is shaped by the interaction of rocks, water, atmospheric gases, and living organisms, especially land plants and microbial communities. On the continents, where early forests and other vascular plant assemblages cover large areas, soils develop as weathering fronts that extend downward from the surface into underlying bedrock and sediment. At the surface, litter from leaves, stems, roots, and reproductive structures accumulates and decomposes under the influence of fungi, bacteria, and soil invertebrates. This decomposition converts complex organic compounds into simpler molecules, releasing carbon dioxide, water, and a range of dissolved ions and organic acids. Carbon dioxide produced in soils combines with infiltrating water to form weak carbonic acid, which moves downward and laterally through pore spaces. As this mildly acidic water contacts mineral grains in the weathered mantle, it reacts with silicate and carbonate minerals. In silicate rocks, cations such as calcium, magnesium, sodium, and potassium are leached into solution, while silica and secondary minerals such as clays form in place. In carbonate-rich substrates, dissolution of calcite and related minerals releases calcium and bicarbonate into solution more directly. These reactions represent the primary steps of chemical weathering, and they proceed more rapidly in the presence of plant roots and associated microbial communities that maintain elevated carbon dioxide and organic acid concentrations in pore waters. The result is a vertical gradient in soil chemistry, with upper horizons enriched in organic matter nitrogen, and certain nutrients and deeper horizons characterized by altered mineral assemblages, leached zones, and accumulations of secondary phases such as iron oxides. Root systems penetrate through these horizons, drawing water and dissolved nutrients upward to support plant growth and returning carbon to the soil when fine roots die and decompose. Nitrogen, an essential element for plant and microbial metabolism, is cycled through these soils by both biological and abiotic processes. Molecular nitrogen in the atmosphere is not directly available to most organisms, so nitrogen fixation by specialized bacteria and archaea, some of which live in association with plants or in free living states in soils and surface waters, converts it into ammonium. This ammonium is taken up by plants and microbes, or transformed by nitrifying bacteria into nitrate. Within soils and saturated zones, denitrifying bacteria can reduce nitrate back to gaseous forms under low oxygen conditions, returning nitrogen to the atmosphere. Phosphorus, derived primarily from the weathering of apatite and other phosphate-bearing minerals, is mobilized into solution and taken up by roots and microbial cells, then recycled through litter decomposition. Because phosphorus tends to bind strongly to mineral surfaces and participate in the formation of secondary minerals, its mobility is more limited than that of some other nutrients, and soils can develop zones where phosphorus availability constrains biological productivity. These element cycles operate within the context of a carbon cycle that connects land, atmosphere, and ocean. On land, plants fix carbon dioxide from the air through photosynthesis, incorporating carbon into organic tissues. Some of this carbon is returned to the atmosphere through respiration by plants, animals, and microbes, while some enters soils as litter and root exudates. In aerobic soil layers, microbial decomposition oxidizes much of this organic carbon back to carbon dioxide, but a fraction can be stabilized through association with mineral surfaces or transport into deeper, less oxygenated zones where decomposition is slower. During floods and surface runoff events, particulate organic matter and dissolved organic carbon are exported from soils to rivers, lakes, and eventually to shallow seas. Rivers thus carry a mixture of dissolved inorganic carbon, dissolved organic carbon, and particulate organic carbon, along with a suite of dissolved ions derived from weathering. As river water enters estuaries, deltas, and coastal seas, physical and chemical gradients promote further transformations. Mixing between fresh and marine waters causes changes in pH and ionic strength that can lead to flocculation of fine particulate material, including organic matter and clay minerals, enhancing their deposition. Within water columns of rivers, lakes, and shallow seas, dissolved inorganic carbon can be taken up again by photosynthetic organisms, while dissolved organic compounds serve as substrates for heterotrophic microbes. Oxygen dynamics are closely linked to these carbon transformations. In well-mixed oxygenated waters, photosynthesis produces oxygen during daylight hours, and diffusion from the atmosphere replenishes oxygen consumed by respiration and chemical oxidation. In soils and sediments, oxygen penetrates only to limited depths, determined by the balance between diffusion and consumption. In the upper oxic zones of soils, aerobic respiration by roots and microorganisms dominates, while deeper layers may become low in oxygen or anoxic, especially in waterlogged conditions. Under such conditions, alternative respiration pathways that use nitrate ion manganese or sulfate as electron acceptors become important, producing reduced forms such as nitrogen gases, ferrous iron, and sulfide. When these reduced species migrate into more oxic regions, or encounter oxidizing agents, they are converted back to more oxidized forms, closing local redox cycles. Shallow marine sediments on shelves and in epicontinental seas display analogous structures. At the sediment-water interface, a thin oxic zone contains burrowing invertebrates and aerobic microbes that consume organic matter delivered from the overlying water. Beneath this zone, oxygen is depleted and suboxic and anoxic layers develop. In these deeper layers, sulfate-reducing bacteria convert sulfate to sulfide, which can react with iron to form pyrite. The formation and burial of pyrite in sediments represents a sink for both sulfur and reduced iron, and has implications for the long-term balance of oxygen in the atmosphere and oceans, because it effectively removes reduced material that would otherwise consume oxygen if oxidized. When rates of organic matter deposition are moderate and mixing by benthic animals is active, the oxic layer remains relatively thick, and most organic carbon is oxidized before burial. When deposition rates are high, water column stratification limits oxygen supply, or benthic faunas are sparse. Oxygen may be consumed quickly near the sediment surface, leading to the expansion of anoxic zones. In such circumstances, a larger fraction of organic carbon escapes complete decomposition and is buried in sediments, contributing to long-term carbon sequestration. In the Devonian time window considered here, evidence from sedimentary rocks indicates that episodes of low oxygen conditions occur in some basins, particularly in deeper parts of epicontinental seas and outer shelves. Black shales rich in organic carbon and pyrite record intervals when bottom waters are anoxic or nearly so and benthic animal fossils are rare or absent. In other basins and time slices within the same general interval, sediments display more mixed fabrics, abundant bioturbation structures and diverse benthic faunas indicating well-oxygenated conditions. This spatial and temporal variability shows that the marine environment is not uniformly oxygen-rich or oxygen-poor, but exhibits a spectrum of states controlled by local productivity circulation basin geometry, and the balance between oxygen supply and demand. Some intervals of more persistent and widespread anoxia in the Devonian broadly coincide with notable changes in marine faunas, including extinctions and community reorganizations, But in this particular slice of time, the focus is on the fact that the ocean atmosphere system has the capacity to move between better ventilated and more restricted regimes, and that soils, rivers, and plant-driven weathering processes contribute to the fluxes that influence these regimes. Nutrient cycles beyond carbon and nitrogen also play roles in regulating productivity and oxygen status. Phosphorus delivered from land can stimulate primary production in shallow seas, increasing organic matter flux to the seabed and potentially enhancing oxygen consumption at depth. If burial of phosphorus in sediments does not increase proportionally, feedbacks can maintain high nutrient levels and sustain elevated productivity. In other settings, efficient trapping of phosphorus in coastal and shelf sediments by adsorption onto iron oxides or incorporation into minerals can limit its availability, constraining productivity and reducing the tendency toward anoxia. Iron itself cycles between oxidized and reduced states, with oxic conditions favouring the formation of insoluble oxides that scavenge phosphate and some trace metals, and anoxic conditions leading to dissolution of these oxides and the release of associated elements back into solution. On land, these processes manifest in the development of soil horizons rich in iron oxides that impart reddish or yellowish colours, particularly in well-drained oxygenated zones. In poorly drained or periodically waterlogged soils, reducing conditions can produce mottled or grey colours as iron is mobilised and redistributed. Such features preserved in paleosols provide evidence for the redox history of ancient land surfaces and their hydrological regimes. Through time, the integrated effect of these chemical and biological processes is to couple the evolution of soils and continental weathering to the composition of rivers and coastal waters and to the state of shallow marine basins. Enhanced weathering driven by early forests increases the flux of dissolved ions and bicarbonate to the ocean, supporting carbonate precipitation and influencing alkalinity. Increased burial of organic carbon in terrestrial and marine sediments acts as a long-term sink for atmospheric carbon dioxide and source of oxygen, although the magnitude and timing of these sinks depend on the balance between production and decomposition in specific regions and intervals. The record around 400 million years ago captures a stage in which these feedbacks are active, but not yet at the extremes seen in some later periods, with soils, rivers, and shallow seas participating in dynamic interconnected cycles of carbon nutrients and redox-sensitive elements that operate over scales from soil profiles and individual basins to the global Earth system. At the microscale in the Devonian interval around 400 million years ago, life and structures in both marine and terrestrial settings consist of organisms and features that are too small to see without magnification, but that collectively exert strong control over physical and chemical conditions. In the oceans, the upper sunlit layer contains large populations of microscopic photosynthetic organisms, including cyanobacteria and various groups of single-celled algae. These cells take up dissolved carbon dioxide and nutrients and convert them into organic matter using light, and they form the base of many food webs. Their sizes range from a few micrometers to a few tens of micrometers, and their shapes can be spherical, elongated, or more complex, sometimes enclosed in organic or mineralized walls. Some algae produce resistant cystages with thick walls that allow survival during unfavorable conditions, and that later become part of the sedimentary record as organic walled microfossils. Alongside these producers, microscopic heterotrophic protists and small metazoans, including tiny crustaceans and larval forms of larger invertebrates, graze on cells and particles suspended in the water. Their feeding activities break down larger particles into smaller ones and transfer organic matter to higher trophic levels, while their own bodies and fecal pellets contribute to the downward flux of material toward deeper layers. In clearer, warm shelf seas, this planktonic layer can be dense with spatial and temporal variability linked to nutrient supply temperature and mixing. Within reef frameworks and on adjacent seabeds, microscale structures include the mineral fabrics of skeletal organisms, the fine-grained carbonate matrix that fills voids, and the microbial communities that occupy pore spaces. Corals and stromatoporoids build skeletons from calcium carbonate arranged in regular patterns of fibres, laminae and pores, at scales of tens to hundreds of micrometers. These internal microarchitectures confer specific mechanical properties and influence how water and dissolved substances move through the living skeleton and the underlying rock. After the death of the organism, the skeletal framework can be partially dissolved, cemented by new carbonate precipitates, or invaded by boring microbes and invertebrates. Microborings produced by algae, fungi and bacteria penetrate skeletal walls, often as narrow, cylindrical or branching cavities, and increase internal surface area. Encrusting organisms, including thin crusts of algae and small invertebrates, grow over exposed surfaces and contribute additional carbonate layers with their own microstructures. Between larger skeletal elements, fine carbonate mud or micrete accumulates. This mud may originate from the disintegration of shells and skeletons and from direct precipitation, and under microscopic examination it appears as aggregates of very small crystals. The combination of skeletal fabrics, cements and macritic matrix gives reef rocks their characteristic textures and porosity, and it is at this scale that many diagenetic changes take place, including recrystallization, dissolution, and the formation of microfractures. On soft seafloors, microscale life includes dense communities of bacteria and archaea that inhabit the upper sediment layers. At and just below the sediment-water interface, oxygen is present, and aerobic microbes oxidize organic matter delivered from the water column. A thin band of sediment may display steep gradients in oxygen, hydrogen sulfide, and other chemical species over distances of millimeters, creating distinct microenvironments. Below this, in suboxic and anoxic zones, sulfate-reducing bacteria and other anaerobic microorganisms perform metabolic processes that recycle sulfur, nitrogen and carbon. Within this framework, filamentous bacteria, coccoid forms and other morphologies form biofilms and mats that bind sediment grains together and produce extracellular polymeric substances. In some locations, especially on tidal flats and shallow shelves, such microbial mats develop at the sediment surface and trap and bind fine particles, contributing to the formation of finely laminated structures. Under magnification, these laminations may show alternating layers of grain-rich and organic-rich material that reflect periodic variations in sediment supply and microbial activity. The accumulation and early lithification of these mats can generate distinctive sedimentary structures that persist in the rock record. In the water column below the photic zone, microscale life continues in the form of heterotrophic microbes that decompose sinking organic matter, and in mineralizing microplankton such as radiolarians and certain calcareous or siliceous algae where those groups are present. Their skeletal remains add to the fine sediment that blankets deep basin floors. Fragments of conodont elements, small tooth-like phosphatic structures derived from eel-like vertebrates, also contribute to the microscopic content of marine sediments. These elements, usually a few millimeters or less in length, show internal and external microstructures that reflect their growth and functional use, and later serve as useful tools for stratigraphic correlation. But in this interval, they are simply components of the fine sediment mixture. On land, microscale structures are equally important. In soils beneath early forests and plant communities, mineral grains, organic matter and void spaces arrange into aggregates, held together by organic coatings, fungal hyphae and fine roots. Under magnification, these aggregates show a complex network of pores, ranging from large channels that allow root penetration to much smaller micropores that retain water against gravity. Bacteria, archaea, and fungi populate these pores and surfaces. Filamentous fungi extend hyphae through the soil matrix, connecting distant points and transporting nutrients and water. Bacteria form colonies on mineral and organic surfaces, where they participate in decomposition, nutrient transformations, and mineral weathering or precipitation. Protozoans and small metazoans feed on these microbes and on each other, adding an additional layer of interactions. The immediate zone surrounding roots, often called the rhizosphere in later terminology, is characterized by strong chemical and biological gradients at the microscale. Root tips exude organic compounds, alter pH in their vicinity, and consume oxygen through respiration. Microbial communities respond by proliferating in these zones, increasing rates of nutrient transformations, such as nitrogen mineralization and phosphorus mobilization. Mineral surfaces near roots may display etching patterns where organic acids and chelating agents have enhanced dissolution. Secondary minerals can precipitate in pores as conditions change, forming microscale coatings and nodules. In seasonal or intermittently waterlogged soils, microscale redox fronts move up and down as saturation changes, redistributing iron and manganese between oxidized and reduced forms, and generating mottled patterns that are only fully resolved at small scales. Fungal hyphae and plant root hairs also stabilize soil aggregates and influence the pathways available for water and air movement. Spores produced by land plants are a prominent microscale component of the Devonian environment. Many vascular plants release large numbers of spores into the air from sporangia located on stems, leaves, or specialized structures. Under magnification, these spores show diverse shapes, sizes, and surface ornamentations. Some are smooth-walled, while others bear spines, ridges, or reticulate patterns, and their walls consist of multiple layers, including highly resistant outer materials. These features influence how spores disperse, how they interact with water films during germination, and how well they withstand physical and chemical stresses. Air over vegetated landscapes contains mixtures of spores, fragments of plant tissues, microbial cells, and mineral dust, and this airborne load contributes to deposition on land and in water bodies. When spores settle into lakes, floodplains, or shallow seas and become buried in fine sediment, their resistant walls allow many to persist as fossils. Palynological assemblages in Devonian rocks thus contain abundant spores that record the taxonomic composition and distribution of plant communities, and at the time they are simply part of the particulate material cycling through the microenvironment. In addition to spores, some microfossils derive from algae, including organic walled cysts, associated with planktonic forms. These cysts, often called palynomorphs in later classification, display a wide range of morphologies, with processes, horns, or other extensions that may aid in buoyancy or in the formation of resting stages. In life, these structures function as resilience mechanisms, allowing cells to survive unfavorable conditions in the water column or in sediments. In the Devonian interval under consideration, such cysts are present in marine and marginal facies and contribute to the reversible storage of biomass in sediments and to the geological record of microscopic marine life. At the scale of individual mineral grains and pores in rocks, microscale features include dissolution pits, overgrowth cements, and fine fractures. In carbonates, early marine and burial cements precipitate in pore spaces as tiny crystals that grow from grain surfaces. Their shapes and arrangements depend on saturation state temperature and the presence of organic molecules that can either promote or inhibit nucleation. Silicate grains in sandstones may show etching along specific crystallographic planes, evidence of selective dissolution under conditions influenced by pore water chemistry and microbial activity. Iron oxide coatings on grains and within pores record past episodes of oxidation, while fine-grained pyrite in framboidal aggregates points to sulfide generation under reducing conditions. All of these microscale features respond sensitively to changes in local chemistry and physical conditions, and once preserved provide a record of those conditions. In shallow marine and marginal settings, microbialites and finely laminated carbonate structures form where microbial communities organize sediment trapping and carbonate precipitation at small scales. Under magnification, these structures can show domal or columnar forms, built from repeated microlaminae of carbonate and organic-rich material. Within each lamina, crystal fabrics and microfossils reflect the balance between microbial growth sediment input and chemical precipitation at the time of formation. Although such structures may look massive at the outcrop scale, their internal organization is dominated by microscale processes. Taking all these aspects together, the microscale world of the Devonian, around 400 million years ago, is composed of densely populated microbial communities in soils and sediments, diverse microscopic producers and consumers in the oceans, highly structured spores and cysts in air and water, and intricate mineral fabrics and pore networks in rocks. These small-scale entities and features govern many of the rates and pathways of chemical reactions, nutrient cycling and energy flow that underpin larger-scale patterns in landscapes, oceans and climate. The macroscopic Devonian world of forests, reefs, fishes and shallow seas rests on this foundation of microscale life and structures, which operate continuously across environments and provide the fine-grained interface between living organisms, fluids and the solid earth. In the Devonian interval around 400 million years ago, the rocks that accumulate on land and in the oceans form the primary record from which conditions in this world are reconstructed. These rocks preserve the physical structures left by flowing water waves, tides and wind, the remains and traces of organisms that live in different environments, and the chemical signatures of the atmosphere, hydrosphere and biosphere as they interact with the solid earth. On continental shelves and in epicontinental seas, carbonate and siliciclastic sediments settle from suspension, move along the seabed, and are reworked by storms and currents. Over time they are buried, compacted and cemented to form limestones, dolostone, sandstones and shales that retain in their internal fabrics a record of the Devonian marine realm. In warm, clear, shallow waters above low-latitude shelves, carbonate production by corals, stromatoporoids and other skeletal organisms is high, and thick successions of reef and platform limestones develop. Within these limestones, individual coral colonies and stromatoporoid bodies appear as distinct masses with recognizable shapes, separated by spaces filled with skeletal debris and fine carbonate mud. Under close inspection, bedding planes show hummocky, cross-stratification wave ripples and graded storm beds that indicate episodic reworking by storm waves and associated currents. In quiet back reef and lagoonal zones, finer-grained mud-supported limestones accumulate often, with bioturbation structures where benthic organisms have churned the sediment. On outer shelves and in deeper parts of epicontinental seas, carbonate deposition may give way to mixed carbonate and siliciclastic sediment, and farther offshore to dominantly siliciclastic muds and fine sands derived from distant continental sources. These siliciclastic successions include laminated mudstones, siltstones and thin sandstones that reflect suspension, settling distal storm reworking and contour parallel flows. In some basins, intervals within these successions are rich in organic matter and dark in colour, representing phases when bottom waters are oxygen poor and benthic faunas are sparse or absent. The fine lamination and lack of bioturbation in such black shales record conditions in which sediment accumulates with little disturbance and microbial decomposition proceeds under limited oxygen. On continental margins where rivers deliver large volumes of sand and gravel near shore, and shallow marine deposits include cross-bedded sandstones with trough and planar sets that preserve the migration of dunes and bars under combined wave and current action. Pebble lags and shell beds mark high-energy events. As water depth increases offshore, these sand bodies thin and fine, grading into siltstones and mudstones, with lower-energy sedimentary structures. In some settings, gravity-driven flows such as turbidity currents transport sediment downslope into deeper basins, generating graded beds with sharp bases and finer tops that stack into turbidite sequences. On land rivers, floodplains, lakes and aeolian systems generate their own distinctive suites of rocks. Fluvial channel deposits form ribbons and sheets of sandstone with internal architectures that include inclined heterolithic strata, point bar accretion surfaces and channel lag conglomerates. Crossbedding, ripple lamination and erosional bounding surfaces reveal the history of channel migration, bar growth and flow variability. Adjacent floodplain deposits consist largely of mudstones and siltstones, with root traces, desiccation cracks and ped structures that reflect soil formation and periodic exposure. In some horizons, upright stumps, in situ root systems and accumulations of plant stems and leaves document former forest stands and vegetated surfaces. Lake deposits include laminated mudstones and fine-grained carbonates that represent settling from quiet water columns. Valve-like couplets of finer and coarser material may signal seasonal changes in inflow productivity or ice cover in higher latitude basins, though the presence and continuity of such patterns depend on local climate and basin geometry. Enclosed or restricted lakes evaporate minerals such as gypsum or halite can form if evaporation exceeds inflow and solute concentrations rise, but the extent of such deposits in the Devonian interval, considered here, is controlled by regional aridity and basin balance. In upland and arid regions, aeolian processes can transport and deposit sand in dunes and sheets, producing well-sorted high-angle cross-bedded sandstones, although the relative contribution of such deposits to the global Devonian record is smaller than that of marine and fluvial systems. Across both marine and terrestrial environments, volcanic activity contributes additional material. Ash falls from explosive eruptions settle over wide areas, blanketing existing landscapes and seafloors with fine pyroclastic material. When these ash layers become interbedded with sediments and later altered to clay-rich layers, they provide time-parallel markers that can be dated radiometrically, offering absolute age constraints within the stratigraphic framework. Lavus and intrusive bodies provide further igneous rock units that, when their magnetic minerals cool through critical temperatures, lock in the direction of Earth's magnetic field at the time of emplacement. Fossils within these rocks supply direct evidence of Devonian life. In marine carbonates, fossils of tabulate and rugose corals, stromatoporoids, brachiopods, bryozoans, crinoids, mollusks, trilobites, and other invertebrates occur as isolated skeletons, clusters or framework components. Their assemblages vary with water depth, energy and substrate type, allowing differentiation of reef crest, forereef, back reef, and open shelf settings. In siliciclastic marine rocks, brachiopods, bivalves, cephalopods, trilobites, and trace fossils such as burrows and feeding trails indicate benthic communities and behavioral patterns. Some fossil groups, such as conodont elements and certain ammonoids, are especially useful for biostratigraphy because they evolve, rapidly, have wide geographic distributions, and occupy specific ranges in time. Geologists use their presence and associations to subdivide the Devonian into finer intervals and to correlate strata between distant basins. Vertebrate remains, including placoderm plates, shark teeth and fin spines, and scales, and bones of lobe-finned and ray-finned fishes, occur in both marine and freshwater deposits. concentrations of vertebrate material in certain beds may represent lag accumulations formed by winnowing of finer sediment mass mortality events, or taphonomic concentration in particular depositional settings such as estuaries or near-shore embayments. On land plant fossils preserve the structure and distribution of Devonian vegetation. In floodplain and lacustrine deposits, compression fossils of stems, leaves, reproductive organs and roots record the morphology of lycophytes, ferns, horsetail-like plants, progymnosperms and other taxa. In some localities, permineralized trunks and branches preserve internal anatomy, including vascular tissues and growth rings. Upright stumps and rooting horizons define former forest floors and soil surfaces. Associated with these plant remains are arthropod fossils, including body segments, exoskeleton fragments, and more rarely complete specimens of millipede, like forms, arachnids, and early insects. Trace fossils such as trackways, burrows, and feeding marks on leaves provide evidence for behavior locomotion and trophic interactions even where body fossils are sparse. Spores and pollen-like structures collectively termed polynomorphs are abundant microfossils in many Devonian rocks. They occur in mudstones, shales, coals, where present and fine-grained carbonates and their resistant walls allow them to persist through burial and diagenesis. Because different plant groups produce distinct spore morphologies, palynological assemblages record changes in vegetation over time and space. Marine polynomorphs, including algal cysts, complement these records and help distinguish marine from non-marine facies. By analysing the vertical and lateral distribution of these microfossils, scientists reconstruct floral and environmental shifts within the Devonian. Beyond paleontology, the rocks from this interval preserve geochemical proxies that constrain past environmental conditions. Ratios of stable isotopes of carbon in carbonates, and organic matter, for example, reflect the balance between different carbon reservoirs and processes such as organic carbon burial and carbonate precipitation. Variations in these ratios through successive beds can mark global or regional disturbances in the carbon cycle, including those associated with episodes of widespread anoxia or changes in productivity. Oxygen isotope ratios in carbonate minerals and in some phosphate fossils provide information with uncertainties about water temperatures and ice volume. Trace element concentrations, including redox-sensitive metals such as uranium, molybdenum, and vanadium, help identify intervals and settings where bottom waters are persistently low in oxygen. In combination with sedimentary facies, analysis such data allow inferences about the extent, duration, and intensity of oxygen, poor conditions in Devonian seas. Paleomagnetic measurements obtained from igneous rocks and some sedimentary units record the direction and polarity of Earth's magnetic field at the time of their formation. When combined with knowledge of how the field approximates a geocentric axial dipole on long timescales, these measurements yield estimates of the paleolatitude at which the rocks formed. By compiling data from many sites and rocks of known age, the positions and movements of continental plates through the Devonian can be reconstructed. These reconstructions in turn provide context for interpreting climatic belts, ocean circulation routes, and the distribution of depositional environments. Radiometric dating of minerals in volcanic ash beds, particularly zircons analysed for uranium-lead, isotopic systems gives absolute ages for specific horizons within the stratigraphic record. When these ages are integrated with biostratigraphic zonations based on index fossils, the temporal framework of the Devonian, including the interval around 400 million years ago, can be placed on an absolute timescale. This combination of relative and absolute dating underpins correlations between continents and oceans and between different depositional settings. Sequence stratigraphic analysis, which examines the stacking patterns of facies and the position of surfaces formed during changes in sea level or sediment supply, further refines understanding of how rock packages relate to transgressions, regressions, and pauses in deposition. Surfaces such as flooding surfaces sequence boundaries and maximum flooding intervals, identified through changes in facies, thickness patterns, and fossil assemblages mark shifts in accommodation space and sediment input. In the Devonian record, repeated cycles of shallow marine transgression over continental interiors and subsequent regression leave characteristic stratigraphic signatures that correspond to changes in the extent of epicontinental seas and coastal environments. Despite this wealth of information, the rock record of the Devonian is incomplete and uneven. Erosion removes portions of the stratigraphy in many regions. Metamorphism overprints primary structures and fossils in others, and some environments, particularly those on steep slopes or in high-energy nearshore zones, are underrepresented because they either do not accumulate thick sedimentary sequences, or those sequences are later destroyed. Preservation biases favour organisms with hard parts, environments with rapid burial, and basins where subsidence allows long-term accumulation. As a result, reconstructions of Devonian conditions at any given place and time rely on integrating multiple lines of evidence and recognizing the limits imposed by gaps and overprints. Nevertheless, taken as a whole, the suite of rocks, fossil structures and geochemical signatures formed during this interval constitutes a coherent record from which the geography, climate, environments, ecosystems and processes of Earth around 400 million years ago can be inferred with significant, though not complete, resolution. In the Devonian interval around 400 million years ago, Earth presents a coherent system in which atmosphere, oceans, continents and living organisms interact across scales from the planetary to the microscopic. From a vantage outside the planet, Earth orbits the Sun within a mature solar system rotating somewhat faster than in the present day and accompanied by a closer moon that strengthens tides. The planet sits at a distance from its star that permits stable surface water, and its axis tilt and orbital motion generates seasons that modulate solar input across latitudes. Continental masses are arranged into a large southern supercontinent, Gondwana, an equatorial to mid-latitude northern continent Euramerica, and several smaller blocks all surrounded by extensive ocean basins. Sea level stands high relative to the average continental surface, flooding wide shelves and interiors and producing broad epicontinental seas. At the scale of climate and atmosphere, nitrogen-rich air contains elevated carbon dioxide and a substantial, though still evolving, share of oxygen. Greenhouse conditions and high sea level combine with the distribution of land and water to maintain a generally warm world with ice-free or nearly ice-free conditions across many high latitudes, extensive warm shallow seas and moist low-latitude belts. Large-scale circulation moves heat and moisture from low to higher latitudes, while regional climates vary with latitude relief and proximity to shallow seas and oceans. On the surface, deep ocean basins occupy most of the planetary area, yet the most biologically active and structurally complex zones lie in shallower regions. Continental shelves, epicontinental seas and coastal margins form continuous belts of low to moderate depth water in which sunlight penetrates the upper water column and interacts with nutrient inputs from land and mixing processes from below. In these settings, microscopic photosynthetic plankton convert dissolved carbon into organic matter, sustaining grazing zooplankton and higher trophic levels. On many low-latitude shelves, corals, stromatoporoids and other carbonate-secreting organisms construct reefs and platforms that host diverse benthic communities of brachiopods, mollusks, echinoderms, bryozoans, and other invertebrates. Soft-bottom shelves and slopes beyond reefs support assemblages of burrowing and surface-dwelling animals that process sediments and influence the penetration of oxygen and nutrients into the seabed. Above the seafloor, nectonic animals, including ammonoids, Other cephalopods and numerous fishes move through the water column as active consumers and predators. Vertebrate faunas include heavily armoured placoderms, early sharks and their relatives, and lobe-finned and ray-finned bony fishes that together occupy a wide range of ecological roles, from small agile feeders in nearshore waters to large predators in open shelf and outer shelf settings. In some basins and intervals, oxygen remains adequate throughout the water column and benthic zones, while in others, especially deeper or more restricted settings, stratification and high organic matter flux drive oxygen depletion near the bottom, producing anoxic layers and organic-rich muds that later become black shales. Along coastlines, transitional environments link land and sea through deltas, estuaries, tidal flats, barrier systems, lagoons, and coastal wetlands. Rivers deliver water-dissolved ions and sediment from interior catchments, constructing deltas where loads exceed the dispersal capacity of waves and tides, and forming estuaries where rising sea levels flood lower valleys. Barrier islands and spits develop where wave reworking shapes shoreline sand into elongated bodies sheltering quieter back barrier basins. Tidal flats and channels record the periodic flooding and exposure set by the tidal regime, and their sediments retain lamination and biogenic structures that reflect repeated cycles of deposition and reworking. In some lowlands, early wetland systems arise where plant cover high water tables and frequent flooding coincide, generating organic rich soils and fine-grained deposits that interact with nearby marine and freshwater environments. Moving inland continental surfaces host a mosaic of early forests, woodlands, scrublands, and more sparsely vegetated zones. Tree-sized plants such as Archaeopteris and other progymnosperms, together with lycophytes, ferns, and horsetail like taxiform, stands on floodplains, low uplands, and some higher slopes. Their roots stabilize substrates, enhance chemical weathering, and explore considerable soil depths, while their trunks and crowns create vertical structure that modifies light temperature and humidity near the ground. In humid regions and along rivers, canopies intercept rainfall and regulate runoff, promoting infiltration and baseflow in streams. On less vegetated slopes and in drier interiors, plant cover is patchier, and erosion remains more vigorous. Across these landscapes, soils develop from the combined action of weathering, biological activity, and hydrology. Organic, rich upper horizons, structured by roots, fungi, microbes, and invertebrates, grade downward into layers where primary minerals are altered and secondary phases accumulate. These soils serve as reservoirs and pathways for water and nutrients, mediating exchanges between solid Earth atmosphere and biota. Terrestrial animal life is dominated by arthropods that occupy forest floors, litter, layers, plant surfaces, decaying wood, and shallow soil zones. Millipede like detritivoras fragment dead plant material and mix it with mineral grains. Arachnids and other predators hunt within litter and on vegetation, and small hexapods and related forms graze on microbial films, decaying tissues, and in some cases living plant parts. Their activities influence decomposition, rate soil structure, and the distribution of organic matter and nutrients at fine scales. In lowland, shallow freshwater systems form networks of streams, rivers, lakes, ponds, and wetlands that connect interior land to coastal margins. These waters carry dissolved weathering products, organic matter, and fine sediment. Freshwater fishes belonging to placoderm, lobe-finned, ray-finned, and acanthodian lineages inhabit channels and basins sharing space with invertebrates that occupy benthic and pelagic niches. Chemical and physical conditions in these systems vary with climate geology and vegetation, yet they consistently act as corridors for material and biotic exchange between land and sea. Within plant bodies, specialized tissues and organs support life on land. Roots anchor plants and draw water and nutrients from soils. Stems provide mechanical support and house-conducting tissues. Leaves expand photosynthetic surfaces, and reproductive structures produce and protect spores. Vascular systems distribute water and solutes through xylem and phloem, while stomata regulate gas exchange between internal tissues and the atmosphere. Life cycles follow an alternation of generations in which sporophyte plants generate spores that give rise to gametophytes, which in turn produce gametes and new sporophytes. In many taxa, spores are similar in size and function, while in others, distinct microspores and megaspores and early seed-like organs appear, indicating diversification of reproductive strategies within this interval. Beneath and around these macroscopic structures, microscale life and features operate continuously. In soils, bacterial and fungal communities, colonize mineral and organic surfaces forming biofilms and networks that promote decomposition, nutrient transformations and mineral weathering. The immediate environment of roots displays strong microscale gradients in chemistry and biology, with concentrated microbial populations and altered mineral surfaces. In marine sediments, microbial processes in thin oxic layers and thicker anoxic zones regulate the fate of organic carbon and redox-sensitive elements. In the water column, microscopic plankton, including algae, cyanobacteria, heterotrophic protists, and tiny metazoans, carry out primary production and grazing, while spores and algal cysts form durable particulate components that move between air-water and sediment. Mineral grains in rocks and sediments bear microscale marks of dissolution, precipitation, and diagenesis that record the passage of fluids and the conditions of burial. Across the planet, cycles of carbon, nitrogen, phosphorus, sulfur, and other elements link these components. Land plants and plankton fix carbon dioxide, soils and sediments store and recycle organic and inorganic forms. Rivers transport dissolved and particulate loads to the sea, and shallow and deeper basins alternately ventilate and restrict bottom waters. Episodes of enhanced organic matter burial in particular basins contribute to long-term carbon and sulfur sinks, while chemical weathering of silicates and carbonates on continents returns cations and bicarbonate to the ocean, supporting carbonate deposition and influencing alkalinity. The balance among these processes during the Devonian interval considered here maintains a warm greenhouse world with extensive shallow seas, expanding forests, and active biogeochemical exchanges. The rock record that forms concurrently integrates these processes at the scale of strata and basins. Marine limestones, shales, and sandstones with their fossil assemblages capture the structure of ocean ecosystems and the chemistry of seawater. Continental sandstones, mudstones, lake deposits, and paleosols preserve river dynamics, floodplain evolution, lake conditions, and the spread of vegetation and terrestrial animals. Volcanic ash layers and igneous rocks provide time markers and paleomagnetic constraints on plate positions. Isotopic compositions and trace element distributions within these rocks encode aspects of climate-ocean oxygenation and carbon cycling. Taken together, these features outline Earth around 400 million years ago as a warm ocean-dominated planet with high sea levels, large southern and equatorial continents, extensive reef and shelf systems, emerging forests and soils, arthropod-dominated land faunas, diverse marine and freshwater fishes, active microscale life and rock sequences that faithfully record the interplay between physical, chemical, and biological processes within this specific Devonian window of geological time.